Welcome to the deep dive. Today we're tackling a really fascinating area where mathematics and physics sort of intertwine.
That's right. We're looking at the idea of reduction.
Yeah, reduction. You could think of it as a way to take these, really complex systems and simplify them. And the key is exploiting their underlying symmetries.
Exactly. It's like finding the hidden structure, the simpler pattern underneath all the complexity. Reduction gives us the mathematical tools to do that.
It's like finding the hidden gears that make the whole machine work, in a way.
That's a great analogy. Often what looks incredibly complicated has, well, a beautiful simplicity if you know where to look.
And today, our deep dive is into a very specific, and I should say, pretty advanced type of reduction. It applies to something called k-contact field theories.
We're going to be working primarily from a recent paper that really digs into this.
Right, and look, the math can get dense, we know that. But our goal here is to pull out the core concepts, the main ideas, and really get a feel for their significance.
Think of this as maybe a shortcut to understanding the key insights of this paper by Javier De Lucas, David Rivas, Silvia Vilariño, and Bartosz and Zawora.
We won't get lost in every single proof derivation, promise.
No, but we will focus on understanding the definitions, the logic, why these things are set up the way they are, and, why it matters.
And this work, it builds upon a pretty well-known technique, right? Marsden Meyer Weinstein reduction.
Yes, MMW reduction. It's a cornerstone. It originally came out of symplectic geometry,
Which is the geometry of phase spaces in classical mechanics, basically. The space of all possible states a system could be in.
Exactly. But MMW reduction has proven much more general, and its reach has expanded into, well, many other areas of math and physics.
At its heart, what's the core idea of MMW?
It's about simplification through symmetry. You take a system, you identify its symmetries, and the conserved quantities that Noether's theorem tells us must exist because of those symmetries.
Right.
And you use that information, specifically through something called a momentum map, to construct a simpler, reduced system that still captures the essential dynamics.
It's really elegant when it works.
It is. And what's exciting about the paper we're looking at is seeing how this established tool, MMW reduction, is being adapted, really extended, to handle these more general geometric frameworks.
It shows the power of these fundamental ideas, doesn't it? How flexible they can be.
Definitely.
And that brings us right to the heart of it. K-contact manifolds. Now, these are generalizations of the more, let's say, familiar contact manifolds.
Well, you might have bumped into contact geometry maybe in thermodynamics or optics. But the crucial thing for today, for K-contact manifolds, is their relevance to field theories that involve dissipation.
Dissipation, like friction, energy loss. Systems where energy isn't conserved.
Exactly. So we're moving beyond those idealized, perfectly conservative systems you often start with in physics.
That seems really important. I mean, real-world systems almost always have some energy loss, right?
Absolutely. It's fundamental. And K-contact geometry gives us the mathematical language, the rigorous framework to actually describe and analyze these more realistic dissipative systems.
Okay, so over the course of this deep dive, we'll be carefully looking at the geometry of these k-symplectic and k-contact manifolds.
We need that foundation.
We'll unpack momentum maps, which intuitively capture those conserved quantities linked to symmetries.
We'll define them carefully.
And we'll really dig into the reduction theorems themselves, step by step, trying to follow the mathematical reasoning. Why do these techniques work? What do they tell us?
Sounds like a plan. Where should we start? The foundational geometry seems logical.
Yeah, let's start there. The paper begins by laying out the basics, starting with k-vector fields and their integral sections.
Yeah.
What's a k-vector field?
Okay, so definition first. A k-vector field on a manifold M is defined as a section of the Whitney sum of k copies of the tangent bundle Tm.
Okay, hold on. Whitney sum, that sounds a bit abstract. Let's try to visualize it.
Yeah.
So at any point on our manifold M, we have the tangent space, right? All the possible directions you can move in, infinitesimally.
Yep, the vector space of tangent vectors at that point.
Now, the Whitney sum, is it like taking tick identical copies of that tangent space at each point and sort of stacking them together, but smoothly across the whole manifold?
That's a very good way to think about it.
Yeah.
You're taking the direct sum of k copies of the tangent bundle, Tm rel, Tpm, Tm rel, k times. So at each point, P and M, the fiber, is Tpm, Tpm rel, Tpm.
Okay. So a k-vector field then isn't just assigning one vector at each point like a normal vector field does.
Right.
It assigns a collection of k-vectors at each point.
Yeah.
One from each copy in that sum.
Exactly. If you have a k-vector field, let's call it X, You can think of it simply as an ordered set, a k-tuple of standard vector fields on M, say x, x1, x2, xk.
Ah, okay, so each exa, where I goes from 1 to k, is just a regular vector field we're familiar with.
Precisely. Each exa assigns a single tangent vector at every point of M. The k-vector field x just packages them together.
Got it. Then the paper talks about the first prolongation of a map. What's that about?
Okay, so imagine you have a map. Let's call it Draco. It takes points from Rk, that's k-dimensional Euclidean space, think of it as parameters like t1, t2, tk, and it maps them to our manifold M. So Rkm, its first prolongation, which the paper denotes as Rk prime, is a new map. It also starts in Rk, but it lands in that Whitney sum bundle we just discussed, Rktm.
So it lands where the k-vector fields live. What information does it capture?
It essentially captures not just where sends a point to Rk to on M, that's just kpm, but also how that image point is changing with respect to each of the k parameters t1, tk.
So it's like position and velocity information, but k velocity is one for each parameter.
Exactly. Let's make that a bit more formal. For a point t1, tk in Rk, the first prolongation is defined as a pair.
Okay.
The first part is just the point on the manifold.
The position.
Right. The second part is a k-tuple of tangent vectors at that point, and these tangent vectors are obtained by taking the tangent map of at t, let's call it t, and applying it to the standard basis vectors in the tangent space of arc at t. Those basis vectors are just euro, evaluated at t.
So, okay, looks like t thorn t, t, t. Precisely, each teratat is a tangent vector to M at the point. It tells you how is changing as you wiggle the ta coordinate in arc. So, neatly packages the map's value and all its first-order partial derivative information.
Okay, that makes sense. It's bundling the point and its tangent vectors with respect to the parameters.
Exactly.
And with that definition, now we can understand integral sections.
Yes. An integral section of a k-vector field X is a map from arc to M, like before, with a spectral property. Its first prolongation must exactly match the k-vector field X composed with the map itself.
So the equation is ox for all t in arc. That's the one. Remember, x is the value of the k-vector field X at the point G on the manifold, which lives in the Whitney sum bundle Eris AT.
Yep.
And ART lives in the same space.
Let's try to visualize that. The k-vector field X gives us like k velocity vectors at every point on M.
Right.
An integral section is then like a k-dimensional surface or maybe a sheet embedded in M.
Parameterized by arc, yes.
Such that the tangent vectors to this sheet in each of the k parameter directions, the t directions, are precisely the k velocity vectors given by the k-vector field X at that point on the sheet.
That's a perfect way to put it. The surface's intrinsic tangent structure perfectly matches the externally defined k-vector field along that surface.
It's like the surface is flowing along the direction specified by X.
Exactly.
Now, the paper mentions a really crucial condition for such a k-vector field X to be integrable. It says the component vector fields x1, x2, xk must commute pairwise.
Yes, xxxco for all pairs x in length.
And the lie bracket, XX, measures how much the flows of XSX fail to commute, right? If it's 0 flowing along XX, then it gets you the same place as flowing along XAT than XAC.
Precisely. Commutativity means the flows associated with the individual vector fields mesh together nicely.
So integrability of the k-vector field means this sort of harmonious relationship between its components. Why is that the condition for finding integral sections?
Because that commutativity condition, XX0, is precisely what ensures that the conditions imposed on the tangent vectors of our would-be integral section are consistent. If they didn't commute, you'd essentially get conflicting requirements on the second derivatives of arc, like xsec needing to equal xs, and you generally couldn't find a smooth map that satisfies xdes everywhere.
Okay. It's the Frobenius integrability condition, generalized.
Exactly. It guarantees the existence of these integral sections, these k-dimensional surfaces, whose tangent structure aligns with the k-vector field.
And the paper links this directly to systems of partial differential equations, PDEs.
Yes. If we write things out in local coordinates, say our coordinates on M, and our k-vector field components are exigary, sum over I implied, and our map has coordinate functions, the exo, so T has coordinates 1, T.
Right.
Then the condition exigary breaks down into a system of first-order PDEs. For each coordinate I and each parameter I, you get XEIC.
Let's parse that. The partial derivative of the ith coordinate function of the map, with respect to the ith parameter.
Of course.
The ith component of the ith vector field making up x, evaluated at the point.
Correct. You have a such equations for each of the n coordinate functions, I. So n times k first-order PDEs in total.
So finding an integral section is solving this system of PDEs.
Exactly. And the integrability condition we just discussed, xxcioo, is precisely the condition from multivariable calculus, equality of mixed partials, that guarantees this system of first-order PDEs has consistent locally unique solutions for given initial conditions.
Wow, okay. That ties the geometry, k-vector fields, integral sections, very neatly to the analysis, systems of PDEs, solvability conditions.
It's a beautiful connection, foundational for field theories, described this way.
Okay, so that sets up k-vector fields. Now let's shift gears slightly to k-symplectic geometry. What defines a k-symplectic manifold?
All right, a k-symplectic form on a manifold, let's call it P this time, is defined as an RK-valued 2 form denoted up.
RK valued again. So like the k-vector field was k-vector fields, this is k regular 2 form.
Exactly. You can think of up as a collection, os1 to up, where each part is a standard differential 2 form on P.
And what properties must these poems satisfy for the collections to be k-symplectic?
2 main things. First, each component 2 form pub must be closed.
Closed means its exterior derivative is 0. Do equals 0 for all f.
Correct. That's the first condition.
And the second?
The second is that the entire RK-valued 2 form must be non-degenerate.
Okay, non-degeneracy. In standard symplectic geometry, K1, that means if a uv equals 0 for a fixed v and all u, then v must be the 0 vector. How does it work for k components?
It's a direct generalization. Non-degeneracy for Ho means that if you have a tangent vector v at some point p in P, and if OUV equals 0 for all other tangent vectors u at P, where that 0 means the 0 vector in RK, so all k components OUV are simultaneously 0,
Right.
then the vector v must be the 0 vector.
So there's no non-zero direction v that is orthogonal to everything else
Right.
with respect to all the forms at the same time.
Precisely. The collection O as a whole doesn't miss any directions. This non-degeneracy is crucial. It ensures, just like in the standard case, a strong connection between tangent vectors and cotangent vectors via the map, V, OUV. This is fundamental for Hamiltonian mechanics.
Okay, closedness of each component and overall non-degeneracy. Got it. The paper then introduces polarized k-symplectic manifolds. What's a polarization?
A polarized k-symplectic manifold, P, is a specific type. First, its dimension has to be of the form n1 plus k for some integer n.
A specific dimension constraint.
Yes. And second, it comes equipped with a special distribution, V, which is a subbundle of the tangent bundle TP. This distribution V must satisfy 2 conditions.
Okay, what are they?
1, V must be integrable. Same meaning as before. The vector fields belonging to V commute, so V defines a foliation of P into submanifolds. The dimension of these submanifolds, which is the rank of V, must be inch.
Integrable, rank inc. And the second condition for V.
The crucial property, the k-symplectic form must vanish completely when restricted to this distribution V, meaning if you take any 2 tangent vectors U and W that both belong to V at some point P, then OUW must be the 0 vector in RK. So OUW equals 0 for all over 1 to k.
So the k-symplectic form is completely blind to directions purely within this special distribution V.
Exactly. It only gives a non-zero result if at least one of the input vectors has a component outside of V. This polarization V adds significant extra structure to the k-symplectic manifold.
Okay. Now, like in standard symplectic geometry, is there a Darboux theorem? Does it say all these manifolds look the same locally?
Yes, there is. Theorem 2.6 is the k-symplectic Darboux theorem. It's a cornerstone result. It applies specifically to these polarized k-symplectic manifolds.
And what does it say?
It says that locally, around any point in a polarized k-symplectic manifold, you can always find a special set of local coordinates. Let's call them E, where I runs from 1 to n and R runs from 1 to k.
Consistent with the dimension n1 plus k.
Right. In these special coordinates, the k-symplectic form takes on a very simple canonical form.
What is it?
It's A GKC A Sedini. Here, the sum is over from 1 to k is the standard basis of RK, and the wedge product is between the coordinate differentials.
Wow, that's remarkably simple. Just sums of wedge products of coordinate pairs, 1 pair for each component pot.
Exactly. And furthermore, in these Darboux coordinates, the polarization distribution V is spanned precisely by the vector fields AGI for all I and I.
So the y coordinates parameterize the directions within the polarization V where OV vanishes.
Correct. This theorem is incredibly powerful. It provides a universal local blueprint for all polarized k-symplectic manifolds. It means locally, they are all indistinguishable from this simple model.
That simplifies things enormously for local calculations.
Immensely.
The paper then gives a key example, right? The Whitney sum of k copies of the cototangent bundle?
Yes, take Q, which is notation for the Whitney sum, k Mario, where take Q is the standard cotangent bundle of some configuration manifold Q.
Just like KQ has a canonical symplectic form.
Take Q has a canonical k-symplectic form, a take Q, and importantly, this canonical form is exact.
Exact meaning it's the exterior derivative of some potential.
Yes, there's a canonical RK-valued one form pay Q, such that take Q, the paper uses a sign convention OU there, which is common in this context.
So TQ, TOQ, is an example of an exact k-symplectic manifold. What do these forms look like in coordinates?
If we use adapted local coordinates key, PQ, or coordinates on the base manifold Q, and PQ are the corresponding momentum coordinates for the F copy of TQ, then the canonical one form is F2Q8E, take key A.
Just the sum of the standard Liouville forms from each copy.
Exactly, and taking the negative exterior derivative gives the k-symplectic form. PQ, KQ, GoQ, TQ, CoQ, A.
Which looks exactly like the k-symplectic Darboux form we just saw, just with a potential sign difference depending on convention and different variable names.
Precisely. The coordinates key PQ are indeed k-symplectic Darboux coordinates for this canonical structure.
And does this example have a polarization?
Yes, it does. The triple TQ, CoQ, VT, KQ forms a polarized k-symplectic manifold. The polarization VTQ is defined as the kernel of the tangent map of the bundle projection TQ.
So VTQ consists of the tangent vectors that point purely vertically in the fibromomentum directions, the ones spanned by OPO.
Exactly. And you can easily check that WebQ vanishes if you plug in two such vertical vectors. So this provides a very concrete, fundamental example of a polarized, exact k-symplectic manifold.
Okay, that's a really helpful model to keep in mind. So we have the geometry. How do we describe dynamics like Hamiltonian systems on these k-symplectic spaces?
Right, that's k-symplectic Hamiltonian systems. You start with a k-symplectic manifold, P. Then you choose a smooth function, HPRR, which you call the k-symplectic Hamiltonian function.
Analogous to the Hamiltonian in classical mechanics.
Yes, the system is then the triple, PRH. The core equation governing the dynamics is the k-symplectic Hamilton-de Donder-Weil equation.
Okay, what is that equation?
It's written as OPX DH.
All right, let's break that down. X is a k-vector field, right? X equals x1, xk.
Correct. ETH is the exterior derivative of the Hamiltonian function h. It's a standard one form on P.
And Euro, what is that map? It takes a k-vector field and gives a one form.
Exactly. Rio is a vector bundle morphism. It maps k-vector fields to one forms. It's defined using the components of O and X, specifically OO X SOHA.
Okay, XFO means the interior product or contraction of the Alth vector field Xs with the Alth two-form form. Contracting a two-form with a vector field gives a one form.
Right, so you do that for each A from 1 to k, and you sum up the resulting one forms. The result is a single one form on P.
So the Hamilton-de Donder-Weil equation, Rho x dh, is asking us to find a k-vector field x such that this specific sum of contractions equals the gradient of the Hamiltonian h.
Precisely. This k-vector field x, if it exists, dictates the evolution of the system.
Does such an x always exist? Is it unique?
Good questions. The paper introduces k-symplectic gauge k-vector fields. These are k-vector fields, let's say y, that lie in the kernel of Euro. So re-y equals 0.
They're invisible to this map.
Right. A k-vector field x that does solve ux dh for some h is called a k-symplectic Hamiltonian k-vector field. Now, if the map Shio happens to be surjective, meaning it can hit any one form dh, then a solution x always exists for any h.
But is it unique?
Not necessarily. If x is a solution, then x plus y is also a solution, where y is any k-symplectic gauge k-vector field, because root x plus y eops x plus UH plus 0 is dh.
Ah, so there's a potential ambiguity up to these gauge fields.
Exactly.
How does this look in those Darboux coordinates we had, Karapi? Let's say on TQ, where ukiyepchi.
Okay, let's work it out. We need AXFSJ, AXPU, AHXP, and DHX, HXHB plus AOKP. Now,
Okay.
BKP, sum over implied. Contracting XXP plus SEA PAID gives.
Exactly, KKMP plus the MTDP.
Okay, A to P. I mean, pay, TQ payout. That's only non-zero if AIK, in which case it's neat. Careful with the indices. Let's stick to Pandashalpi. Then iksha oyi jeshoksi plus sishobo jikishobai.
Right.
The first term gives the expo. The second term gives zeshojeshoj. So iksho, ikshadeshojesho.
Okay.
Now we sum over I kanjali x, section of the patch. And this must equal d shacha, dqj plus bachestra.
Comparing coefficients. The coefficients of the poj must match. So
Exactly. That determines the key components of all the vector fields, like.
And the coefficient of dqj must match. So xshach, xshe. Let me recheck the paper's convention for O and the equation. They use diatricojejo or dkja. Let's redo it with that minus sign.
Okay. Xujde.
Then xshotepaj.
Okay.
Summing over xshotjeja.
Xujde.
Now set that equal to dqj plus jkpaj.
Comparing dikshot jabiyashans gives shotve, or jasot.
And comparing dqj coefficients gives dkoj.
Okay, wait. The paper's description, just below def 2.8, writes the Hamiltonian k-vector field components slightly differently in Dardu coordinates. Let's look at that. They say XS should have the form xik plus subdyuki with the specific condition that's a kane.
Okay, let's see if that x satisfies xkichu with sikoya ekiji.
Right, so it's azadyuki uj plus sexupo.
Applying the contraction rules.
We get tekapaj plus xcgj.
Okay.
Now sum over x seksha dkg plus cg2j.
And we need this to equal dqj plus xej.
Comparing dqq efficients, xpaj needs to equal xpaj. That only works if xpaj chi. That can't be right. Let me reread the definition of Yuri.
Maybe the sum is implicit differently.
Wait. The equation EO10, D means earth axio eat D. Let's re-examine the result of the contraction axio. X at the pen, xpate decurtenge using OX dueli.
So, coxe decurche, this must equal decurche plus the punch.
Comparing coefficients. For the punch, we need xe don page. So the punch extend. This matches the first part of the paper's expression for x if we swap the sign convention on perhaps.
Nice.
Let's assume their expression x ekerche is correct.
Okay, if x has a chi as its q component.
Let's use the paper's stated form. Xyoki plus saktisupod. Well, let's plug this into x. Xyoda, still using ho dohyu.
Xyoya, xk plus dikuchete.
Ekuche doje.
Boix dikuche.
Xyon dikuje dwokije.
Dikyo koche doi plus dikoche. C face with plus 3.
Echorio plus is dikuje ton.
Now sum over x.
Yeah.
Ekoj doi plus sakeche. We need this to equal doche dqj plus dqj.
Comparing dqj, xuj, this doesn't immediately seem to follow from the condition. There might be a subtlety in indices or summation here, or maybe the paper's description is slightly simplified.
Okay, but the general idea is clear.
Yeah.
The equation qjdh relates the components of the k-vector field x to the partial derivatives of the Hamiltonian h via the k-symplectic form.
Yes. And importantly, the paper points out that even if x is a k-symplectic Hamiltonian k-vector field, it satisfies the equation, it's not guaranteed to be integrable.
Meaning the components x1 at ka might not commute pairwise.
Yes.
xj, xeo 0.
Correct. That condition needs to be checked separately.
Why does integrability matter here? Proposition 2.9 connects it to solutions.
Exactly. Proposition 2.9 says, if you have a polarized k-symplectic Hamiltonian system, AXH, and you find an integrable k-symplectic Hamiltonian k-vector field x for it.
So it satisfies EHAND x xc is 0.
Yes. Then any integral section of that x, a map RKP satisfying a k-symplectic is automatically a solution to the Hamilton-Dedonder-Weyl field equations. These are a specific system of PDEs involving Hamo and H detailed elsewhere.
So integrability of the Hamiltonian k-vector field is the key to finding actual solutions that describe the evolution of the fields.
Precisely. Without integrability, you might have the velocity field x, but you can't necessarily integrate it to find the flow bound.
Okay, that clarifies the role of integrability in this context. It's not just a mathematical curiosity.
Not at all. It's essential for finding solutions.
All right. We've covered k-vector fields, k-symplectic geometry, and the associated Hamiltonian systems. Now let's turn to the other main geometric player, k-contact geometry.
Okay. K-contact geometry.
The definition starts with some preliminary concepts. Smooth and regular generalized subbundle. Let's break that down.
Right, a generalized subbundle D of some vector bundle E over our manifold M. It's smooth if, locally, you can find smooth sections of E, like vector fields of ETM, that span D at every point in that neighborhood.
So it's smoothly varying.
And it's regular if it's smooth and it's rank. The dimension of the fiber D inside E is constant everywhere on M. So no sudden jumps in dimension.
Okay, a well-behaved sub-object within the vector bundle. Then they mentioned one-forms defining codistributions and their annihilators.
Yeah, that's standard setup. A one-form E on M naturally defines a codistribution. E's in the cotangent bundle. TM, basically. At each point, it's the line spanned by E.
And its annihilator, E.
That's a distribution in the tangent bundle, TM. A keyword consists of all tangent vectors V such that EE equals 0. If E is non-zero, the C-query is a hyperplane distribution codimension 1.
Okay, basic differential geometry. Now, the definition of a K-contact form, it's an RK-valued one form on some open set Ienia.
Yes, so again, think of E as a collection of K standard one forms, EU, EBE, or ONIA.
And it has to satisfy three conditions. What's the first one?
Condition 1. The kernel of E, denoted Carania, must be a regular distribution of current K.
Let's unpack Kerr first. Since E is RK-valued, Carene must be the set of tangent vectors V that are annihilated by all components simultaneously. EO0 for all on O for KK.
Exactly, that's the kernel. And this kernel must be a distribution, smoothly varying subspace of the tangent space at each point, and be regular, constant rank. Correct means its dimension is dim here.
Okay, so Carene is a well-behaved distribution of dimension NEO if dim NA is condition 1, condition 2.
Condition 2 involves the exterior derivative of E, which is D. Since E is RK-valued, D is an RK-valued 2 form. D is the C EO.
Right.
The condition is that the kernel of D, denoted Ker-ID, must be a regular distribution of rank K.
Okay, Ker-D is the set of tangent vectors V such that dVW is 0 for all other vectors W, meaning dOV for all I and all W.
Actually, Ker-D is usually defined slightly differently for forms. It's the set of vectors V such that dV0, meaning of dia, meaning of D equals 0 for all. This implies dIVW for all W.
Ah, okay. So Ker-D contains vectors V that, when contracted with D, give 0. And this kernel must be a regular distribution of dimension K.
Correct. So we have Ker-D with dimension NK and Ker-D with dimension K.
That adds up to N. What's the third condition?
Condition 3 is crucial. The intersection of these two kernels must be only the 0 vector, Ker-D 0.
No non-zero vector can be simultaneously in the kernel of E and in the kernel of D.
Exactly. This condition reflects the maximal non-integrability idea that's central to contact geometry. It ensures the structure is twisting appropriately.
So 3 conditions. Ker-D has current K, Ker-D has rank K, and their intersection is trivial. If a manifold M admits such an RK-valued one-form E, then M is a co-oriented K-contact manifold.
Correct. The co-oriented part comes from the fact that E itself provides an orientation for the quotient bundle TM, Corey.
And there's also a polarized version.
Yes. A polarized co-oriented K-contact manifold, M, Y, Phi, requires a specific dimension for M, namely N plus Enc plus K for some positive integers N and K.
That looks like the k-symplectic dimension plus K.
The k-symplectic dimension was N1 plus K. This is N plus Enc plus K, N1 plus K plus K. So it's K dimensions larger.
Interesting.
And what else defines the polarization V?
V has to be an integrable distribution, so it defines a foliation, which is contained within Kerr, so E of E equals 0 for all V and all I, and V must have rank and Enc.
Okay, so similar to the k-symplectic case, we have this special integrable distribution V, but here it lives inside Kerr.
Exactly.
The paper notes that for K1, a one-contact manifold is just a standard contact manifold.
Yes, if K1 is just a single one-form eq1, Kerr has Kerrank1, D1 has rank 1. No, that can't be right for standard contact. Let's reread condition 2.
Pralini is a regular distribution of rank K if K1, Kerr has rank 1. And condition 3, puncher. For standard contact geometry on a 2n plus 1 dimensional manifold M is a contact form if ER fail is nowhere 0. This implies D restricted to Kerr is non-degenerate. The kernel of D as a map on vectors VA is called the characteristic distribution. For contact forms, this kernel is typically 0 unless D itself is degenerate, which isn't the case here. Let me check the paper's definition of Kerr again.
Maybe Kerr DAE equals EB.
Yes, that's standard. For a contact form on M2M plus 1, D has rank Touré everywhere. Its kernel is one-dimensional, spanned by the Reeb vector field R. So for K1, the condition Curta has rank K1 seems to align with the existence of the Reeb field.
And Kerr A is a two-dimensional distribution. The Reeb field R satisfies ER, so R is not in Kerr.
Yeah.
Therefore, Kerr A AR is being ER. Okay, it seems consistent.
Good, thanks for working through that. So yes, K1 recovers standard contact geometry, excluding the one-dimensional case, which is trivial.
Now, Theorem 2.12 talks about these Reeb vector fields for the general K-contact case. It says they exist and are unique.
Yes, for a co-orientable K-contact manifold M, there exists a unique set of K-vector fields, R1, R2, Rk, called the Reeb vector fields.
What defines them? What are their properties?
They're characterized by two sets of conditions. First, their relationship with E Reeb vector.
Okay, Reeb means plugging the auth Reeb field Ra into the auth component one form E. The result is one if ER and or otherwise Kronecker delta. So Ra is sort of dual to Ia?
In that specific sense, yes. The second set of conditions relates them to D. E-Re D, E-Rho for all R.
So plugging any Reeb field Ra into the Rk value 2 form D gives 0. This means Ra belongs to Kerr D for all A.
Correct. The theorem further states that these Reeb vector fields commute. Ra equals 0 for all A.
They commute. That's nice.
And their span at each point is exactly the kernel of D, which we know has rank K. So R1 forms a basis for Kerr D at each point.
And finally, their wedge product R1 arrow is nowhere vanishing, confirming they are linearly independent everywhere.
Exactly. These Reeb fields provide a canonical commuting frame associated intrinsically with the K-contact structure. They live in error D, but are transverse to Kerr.
They seem pretty fundamental. Okay, the paper then defines another map, Ray, for K-contact manifolds. What does it do?
This remap takes a K-vector field V equal V, V1, area V, and maps it to something slightly different than the k-symplectic case. It maps to an element in the direct sum T-M-E, M-A-R, where R is just the real numbers.
Okay, so the result is a pair, a one form, and a function.
Basically, yes. The map is given by area V. Area ni by E, area.
The first component looks like the era map using D instead of rho. The second component is new, summing the contractions of the vector components with the one-form components.
Correct. And an Erie gauge K-vector field is simply a K-vector field V that lies in the kernel of this air map. So both components of the result are 0.
Got it. Example 2.14 then gives a concrete example of a K-contact manifold.
Yes, a very natural one. It considers the manifold M, H-E-O-T-A-R, that's the Whitney sum of K copies of the cotangent bundle of Q times Rk.
So it takes the canonical K-symplectic manifold TQ and adds an arc factor.
Exactly. On this M, they define the K-contact form EQAAAAA.
Let's unpack that. Za are the standard coordinates on the arc factor.
Yes, and I is the pullback of the canonical Liouville 1 form, P-T, from the auth copy of TQ in the sum Rk2.
So EA is a P key sum on I. This is very much like the standard contact form DTP-DQ on TQXR.
Precisely. It's the natural generalization. The paper verifies this EQ satisfies the three conditions. It also notes this manifold has a natural polarization V, the vertical distribution from TQ of rank Q, which lies in KDQ.
And the Reeb fields?
They are simply written as the coordinate vector fields for the arc factor. You can check AAAR day. And E as a DT since stock only involves Q's and P's. And clearly AR is vets, which all...
So this URI, TQ, S with TQ, Certi, E is a nice explicit model of a polarized, co-oriented K-contact manifold.
Yes. And just like in the symplectic case, there's a Darboux theorem.
Theorem 2.15, the K-contact Darboux theorem. Does it say this example is the local model?
Essentially, yes. For any polarized, co-oriented K-contact manifold, MEV, around any point you can find local coordinates, Ki, Pi, Z.
Where it goes from 1 to N or from 1 to K, consistent with the dimension N plus K.
Right, such that the K-contact form takes the simple canonical form, E, Z, Ridiki.
Exactly. Love for the example.
Exactly. And in these coordinates, Ticker is spanned by the Reed fields, and the polarization V is spanned by the Erub fields.
Beautiful. Another powerful local normal form theorem.
It really simplifies the local picture.
Okay, geometry established. Now for dynamics. K-contact Hamiltonian systems. How are they defined?
A K-contact Hamiltonian system is a triple MH, where ME is a co-oriented K-contact manifold, and H is a smooth, real-valued function on M called the E-Hamiltonian function.
Simple enough. What are the equations of motion? The K-contact Hamilton de Donderweil equations.
These equations are typically written for a map URKA, which represents the field configuration, the equations involve the first prolongation, fair, and the Reeb fields, Ra. They are given as a pair of conditions for each A from 1 to k.
What are they?
First, a fair dia refers to the th component tangent vector of the first prolongation. A, right? Like test dot.
Yes. E and dia are the oth components of E and D. Ra is the derivative of H along the Reeb field Ra, that is Ra, and A means evaluate the forms or functions at the point 2.
So the first equation relates the contraction of the velocity of 4 with the 2-form dia to the gradient dA, but modified by a term involving the Reeb derivative of H and the 1-form me. Correct. The second equation relates the contraction of the velocity saw with the 1-form ia directly to the value of the Hamiltonian H with a minus sign.
These look significantly different from the k-symplectic equation Ix, A equals dH. The Reeb fields and the Hamiltonian itself play a much more direct role in the equations.
They do. This reflects the different underlying geometry. The Reeb fields are intrinsic to the k-contact structure.
How do these equations look in the k-contact Darboux coordinates k, p, z?
If we write the map using coordinate functions, say I, ph, a, I, and t, say I, these two abstract equations translate into a specific system of first-order PDEs for these component functions. The paper gives the explicit form, equations 2.6. They involve partial derivatives of h with respect to q, p, and z coordinates.
So solving for the field means solving this system of PDEs derived from the Hamiltonian H and the canonical k-contact form.
Exactly.
The paper also gives an equivalent formulation using a k-vector field x equals 1, xk, right? The equation's 2.7.
Yes, similar to the k-symplectic case, you can write down conditions directly on a k-vector field x that should generate the dynamics. These equations, 2.7, involve contractions like x(d) and x(t), relating them to dh and h.
And what are the equivalent relations, 2.8 in Darboux coordinates? Do they constrain the components of x?
Yes, equations 2.8 show how the components of x written in the h-Arab basis are related to the partial derivatives of the Hamiltonian h, ekbini, and the Hamiltonian h itself. These relations essentially define the k-contact Hamiltonian k-vector field x associated with h.
And crucially, proposition 2.18 connects these two viewpoints again.
Yes. It states that if you have an integrable k-vector field x, so x Ziller-Wöhler, then its integral sections satisfy the k-contact Hamilton-de Donderweil equations for a map, EQ's 2.5, if and only if the k-vector field x itself satisfies the k-contact Hamilton-de Donderweil equations for a k-vector field, EQ's 2.7.
So again, integrability of the Hamiltonian k-vector field x is the bridge. It guarantees that the flow generated by x actually solves the field equations written for the map.
Precisely. Integrability remains key for finding solutions.
Example 2.1 in Ike then shows this in action with the coupled damped wave equation. How does that work?
They start with a specific k-contact manifold related to HE, RQ, RK, and a Hamiltonian H. They then construct a corresponding k-contact Hamiltonian k-vector field x using the relations 2.8 by making specific choices for some arbitrary functions that appear in the general form of x and setting others to 0. They arrive at a particular k-vector field x that turns out to be integrable.
Okay, so they found a commuting set of Hamiltonian vector fields for this system.
Yes. Then, according to proposition 2.18, the integral sections of this x must satisfy the field equations, EQ's 2.5 or 2.6. They write down the system of PDEs that the components of P must satisfy, EQ's 2.13.
And these PDEs are equivalent to the damped wave equation.
After some manipulation and elimination of variables among those PDEs, yes, they recover the coupled damped wave equation. It's a concrete demonstration that this abstract k-contact Hamiltonian formalism can indeed describe physically relevant dissipative systems like damped waves.
That's a great payoff. Seeing the abstract machinery connect back to a familiar physical equation.
It really validates the framework.
Okay. So we've laid out the geometry and dynamics for both k-symplectic and k-contact manifolds. We're now finally ready to tackle the main event, reduction. We'll start with the reduction of exact k-symplectic manifolds. Remind us what exact means here.
An exact k-symplectic manifold, P, is one where the k-symplectic form can be written globally as the exterior derivative of an RK-valued one form, so d.
Like A in the standard symplectic case.
Exactly. It implies O is closed, since D is 0, but it's a stronger condition than just being closed.
Okay. Now, k-symplectic momentum maps. How are they defined in this exact setting? We need a Lie group G acting on P, right?
Yes, we need a Lie group action, G, A, P, P. We also need this action to be an exact k-symplectic Lie group action. This usually means it preserves the potential one form, maybe up to an exact form or constant. If it preserves exactly, then it automatically preserves LD.
Okay, so we have P, exact k-symplectic, and an exact actionate. What's the momentum map?
The exact k-symplectic momentum map is defined as a map from the manifold P to the space. That's kp copies of the dual of the Lie algebra G of G.
Okay, P. What equation defines it?
The defining equation is APSD. This must hold for all elements in the Lie algebra G.
All right, let's parse this again carefully. ASP is the fundamental vector field on P generated by L to P. It's how points move under the infinitesimal action.
Correct.
ASP is the contraction of the RK-valued one form with this vector field P. The result is an RK-valued function on P.
Yes.
Now the right side, ASB, JSP, is a point in RK. AC is an AHE. How does the pairing work here to give an RK-valued function?
We think of JA as a k-tuple, J1P, where each J is in G. The pairing AJ is defined as the arc vector, whose arc component is the natural pairing outgo between J and J.
Ah, okay. So the defining equation AJ means that for each component, from 1 to k, the contraction APA must equal the function PAHA.
Precisely. It ties the infinitesimal group action, via AOP, and the potential to this map J taking values related to the Lie algebra's dual.
The paper then contrasts this with the momentum map for a general, not necessarily exact, k-symplectic action. Remind us of that definition.
So our general k-symplectic manifold, PA, and an action that preserves O, or infinitesimally likes P0, the k-symplectic momentum map, MO, the k-symplectic momentum map, AJG, is defined by the equation HA, AJ, ISA.
So here, contracting AP with a 2 form gives the negative exterior derivative of the pairing OJ. It involves a directly, not a potential O, and has that A on the right side.
Exactly. These two definitions are related. If is day and the action preserves is s, then applying day to the exact momentum map equation is k s day, and using less p0, which implies is p is versus do, you can recover the general momentum map equation is to j sa with day to j. So the exact definition is consistent with the general one when an exact potential exists.
Okay, good. Now, equivariance. Definition 3.5 defines an as k equivariant momentum map J. What does that mean?
The Lie group G acts on its Lie algebra G via the adjoint action add J. This induces a dual action on the dual space G, called the co-adjoint action add G. Since our momentum map J takes values in J, add J equivariance means the map respects these actions, specifically J is J ad D phi. Let's break that down. If we first act on a point P with a group element G, getting ed J, and then evaluate the momentum map, we get the same result as if we first evaluate the momentum map at J, getting J, and then act on that result in J to K with the inverse coadjoint action at J1. Exactly. The AJ1 acts on each of the K components of JJ and JJ. It's a natural compatibility condition between the action on P and the action on JJ.
Is this something we usually have to assume? Proposition 3.6 seems important here.
Very important. Proposition 3.6 says that if you are in the exact k-symplectic setting, with an action that preserves, so senche, then the associated exact k-symplectic momentum map is automatically a JG equivariant.
Well, that's nice. For exact systems, equivariance comes for free with the definition of the momentum map. We don't need to impose it as an extra condition.
Correct. It simplifies things considerably in the exact case.
Okay, so we have momentum maps, exact and general, and the notion of equivariance. Now, how do we use them for reduction? The paper first discusses k-symplectic reduction by a submanifold.
Right. This is a slightly more general setup before getting to the MMW theorem itself. We need the concept of the k-symplectic orthogonal.
Orthogonal, okay. If we have a subspace WAP inside the tangent space, TPP at a point P, its k-symplectic orthogonal, WOKP, is the set of all vectors VP and TPP such that OPP is 0 for all WP of 1.
Yes, but remember, OMIP is RK valued, so OMIP VP must be the 0 vector in RK, meaning ORP VP equals 0 for all OMIP and for all OMIP in YK.
Got it. Orthogonality with respect to all K components simultaneously.
Correct.
Now, for reduction using a momentum map J, PP, we often focus on level sets, right? With a set of points where J equals some specific value in RK.
Yes, and for reduction theorems to work nicely, we usually need it to be a regular value, or at least a weak regular value of J. The paper uses weak regular K value. What's the K part add?
It's a bit stronger. It means that ORN has to be a weak regular value for each individual component map, J. BA in itself has to be a weak regular value for the full map, J.
Why both?
Weak regularity ensures the preimage J is a nice submanifold. Requiring it for each component as well likely ensures better behavior related to the individual forms.
Okay, so is a weak regular k-value, J1, is a submanifold. Now, Theorem 3.8, k-symplectic reduction by a submanifold. What does it say?
It considers a more general situation. Let S be any submanifold over k-symplectic manifold, P with inclusion map E. SP, we can restrict the k-symplectic form to S, giving EO.
Okay, this restricted form might be degenerate now.
Exactly. We look at the kernel of this restricted form, KEO. This defines a distribution, possibly of varying rank, on S. Let FS be the foliation defined by this kernel, assuming it integrates nicely.
So we're considering the directions within S where the restricted k-symplectic form degenerates.
Yes. The theorem says, if this kernel K has a Kenner rank on S, and if the quotient space SFS, the space of leaves of this foliation, is itself a manifold, and if the projection map KAS, SFS is a submersion.
Lots of technical conditions ensuring everything is well behaved.
Right. Then the theorem concludes that there exists a unique k-symplectic form AS on the quotient manifold SFS.
A k-symplectic form on the reduced space, how is it related to the original?
It's related by the projection. Says, pulling back the reduced form, OS to S, gives exactly the restriction of the original form O to S.
Okay, so this theorem gives conditions under which we can take a submanifold S, quotient out the null directions of the restricted k-symplectic form, and end up with a new, well-defined k-symplectic manifold.
Exactly. It's a general mechanism for reduction.
Now, how does this relate to the Marsden Meyer Weinstein theorem?
Theorem 3.1 is the Marsden Meyer Weinstein reduction theorem for k-symplectic manifolds. It applies this general idea to the specific submanifold S, the level set of the momentum map.
Ah, okay, so S is just one. What are the conditions?
We need one, is a weak regular k-value of an added k-equivariant k-symplectic momentum map Jess. Ensures S is a nice submanifold.
Got it.
The stabilizer subgroup G Jess must act freely and properly on the level set S as Jess, ensures the quotient SG is a well-behaved manifold, the reduced space P.
Okay, standard MMW conditions generalized. What's the conclusion?
The conclusion is that the reduced space P is itself a k-symplectic manifold.
And it inherits a k-symplectic form.
Yes, there exists a unique k-symplectic form OM on POO such that the P. Here O is the inclusion G P and poses the projection J key. Same relation as in the general theorem.
So the MMW theorem basically says that if the symmetry group G acts nicely on the momentum map level set, then the quotient space naturally inherits the k-symplectic structure.
Exactly. The theorem statement also mentions conditions 3.5 and 3.6 relating the kernel of their restricted form to the tangent spaces of the G orbits. What's their role?
Those conditions essentially ensure that the directions we are quotienting out by the G orbits are precisely the null directions of the restricted k-symplectic form on the level set. Here EPG, APP. This is what guarantees that the form OM on the quotient space will be non-degenerate.
So the group action directions are exactly the bad directions for the restricted form, and quotienting by the group action removes them perfectly.
That's the core idea. The paper mentions these conditions are sufficient, but perhaps not strictly necessary, referencing work by Blacker and others for more refined conditions. But they capture the essential geometric requirement.
Okay. That gives us the standard MMW theorem for general k-symplectic manifolds. Now, the paper modifies this specifically for exact k-symplectic manifolds. Why the need for a modification?
The main reason, looking ahead, is to connect this reduction procedure to the reduction of k-contact manifolds. There is a known link between k-contact geometry and certain exact k-symplectic manifolds involving an extra R factor. To make that link work smoothly for reduction, they need to adapt the k-symplectic reduction framework.
So it's motivated by the eventual goal of k-contact reduction. What's different in this exact MMW version?
A key difference is the set they consider for reduction. Instead of the level set J11 using the exact momentum map J, they look at a larger set.
Right work.
Rec. What does that mean? Is it points P, where J is a scalar multiple of 1? Not quite scalar multiple. Rec 1, man 1, man 1, B1, where rack is the non-zero real numbers and those are 1, 1. So it's the set of points where each component J is a non-zero multiple of the corresponding component Y.
Oh, okay. So we're looking at the preimage of this cone generated by M. Why this set?
It relates to the structure that arises when lifting k-contact manifolds to exact k-symplectic ones, which involves an R scaling factor. This choice anticipates that connection.
Okay, so the reduction happens on J when O. What group do we quotient by? It's not G anymore.
No, it's a different subgroup K related to a specific Lie subalgebra Co.
Proposition 3.12 defines Co. What is it?
Co is defined as the intersection of two subspaces of the Lie algebra G. First is Kerjira Ashali for all island.
That's the annihilator of Ologia.
Okay, and the second subspace.
Second is G manified Schwarz.
Oh, whoa. Adjum is the infinitesimal coadjoint action. Adj is an element of Yo. What does adjum mean? The wedge product of two elements in J. In this context, for ing equals 1 in Ser equals 4 means Syrian is 1 for all equals 1 phi. Or perhaps it means the arc vector, Rk op of t, or perhaps it means the arc vector O you make 1 or satisfies some condition. Let's reread the definition of Goe carefully. It seems a Dao is shorthand for requiring that a Ja is linearly dependent on EU for each ES separately. That is, a Da for some scalar echo phi for each up.
Okay, so Ge contains Ek-Hor if the infinitesimal coadjoint action of on each I just scales or.
Yes, that seems more plausible interpretation in this context. And coin is the intersection. Kol-Kor e.g. Proposition 3.14 proves this intersection. Koi is a Lie subalgebra of G closed under the Lie bracket.
And K is the corresponding connected Lie subgroup.
Yes, K is the connected Lie subgroup of G whose Lie algebra is Koi. This K is the group we will quotient by in the exact reduction theorem.
So the theorem will say J1 is the reduced space.
Pretty much. But first, lemma 3.13 establishes a vital link. It shows that the tangent space to the orbit K for point P in the level set Chang-Jurek is contained within the kernel of the restricted k-symplectic form on that level set.
So TP-KP, or the inclusion of J into P.
Exactly. This is crucial because it means the directions we plan to quotient by the k-orbits are indeed null directions for the restricted form, suggesting the quotient might inherit a non-degenerate structure.
How is that lemma proved?
The proof involves using the definition of cone, particularly the Kerr condition, and the fundamental relation EPK-Jane-Arsha. By differentiating the momentum map along the k-orbits and using the properties of the Lie algebra com, they showed that the tangent vectors to the orbits satisfy the condition required to be in the kernel of Verda restricted to the level set.
Does the kernel of the restricted Ho equal the tangent space to the orbit, like in the standard MMW case?
The paper notes that, just like before, this equality doesn't necessarily hold in general. TP is contained in the kernel, but might be smaller.
Okay. Then there are several technical lemmas, 3.15, 3.16, 3.17. What's their purpose?
They build the machinery needed for the main theorem's proof. Lemma 3.15 is about linear algebra involving surjective maps and symplectic spaces. Lemma 3.16 shows how to define unique symplectic forms on quotient spaces related to kernels of Ba and its restriction. Lemma 3.17 provides identities about orthogonal complements and momentum map kernels, essential for analyzing the tangent space structures.
And proposition 3.18 uses these to show something is a symplectic vector space.
Yes, it shows that a specific quotient space, VPA, constructed from the tangent space of the level set and the action of the Lie algebra car related to a single component, is indeed a symplectic vector space. This confirms that the building blocks for a k-symplectic structure exist in the quotient.
Okay, all the pieces seem to be in place. Now for theorem 3.1 the Marsden Meyer Weinstein reduction theorem for exact k-symplectic manifolds. State it for us.
Theorem 3.19 says, let P be an exact k-symplectic manifold with an exact action and momentum map J. Let it be a weak regular k value of J. Assume the group K, with Lie algebra, Cartan, JG, acts freely and properly on the level set Maremo.
Okay, those are the conditions.
Then the conclusion is, the reduced space P, J-Co, is an exact k-symplectic manifold.
It's exact too, so it has a potential.
The theorem states it has a k-symplectic form, so yes, it's exact. And this reduced form relates back to the original KO via phi, where E is the inclusion and high is the projection.
Fantastic. So we have a robust way to reduce exact k-symplectic manifolds using this modified level set in the group K, and the result is again exact k-symplectic.
Exactly. The proof relies heavily on the preceding lemmas to show the quotient is a manifold, and the reduced form is well-defined and non-degenerate. Lemma 3.22 provides some necessary and sufficient conditions related to the surjectivity of maps involved in the proof, confirming the technical details work out.
This theorem seems like the crucial stepping stone we needed.
It is. It provides the machinery for the final act, k-contact reduction.
All right, let's do it. Marsden Meyer Weinstein reduction for k-contact manifolds. First, we need k-contact momentum maps. How are they defined?
We start with a k-contact manifold, M, and a Lie group action, a AM. The action must be a k-contact Lie group action, meaning it preserves the k-contact form. AG, for all GMG.
Okay, a symmetry that respects the k-contact structure.
Then the k-contact momentum map is defined as a map MDK given by the equation. AG. This holds for all A's in the Lie algebra G.
This looks very similar to the exact k-symplectic momentum map definition, using the k-contact 1 form instead of the potential.
Exactly the same structure. OIG is the RK-valued function obtained by contracting U with the fundamental vector field AG, and OIG is the RK-valued function whose auth component is OIGO, AGO.
Does this k-contact momentum map have a relationship with D, similar to how the general k-symplectic one related to AG?
Yes. The paper shows that if XE is a k-contact Lie group action, preserves S, then it follows that SMD SX.
Oh, okay. Contracting SM with the 2-form D gives the negative exterior derivative of the momentum map pairing. This looks just like the general k-symplectic momentum map definition, XB instead of ERS, but using D instead of Os.
It's a very pleasing parallel structure.
Then the paper defines a G-invariant k-contact Hamiltonian system. What does that entail?
It's a system AASH where we have the G action preserving the associated k-contact momentum map D, and an E Hamiltonian function H, which is also invariant under the group action, X or all G and G.
So the Hamiltonian doesn't change under the symmetry action. Makes sense.
Now, before the MMW theorem, they discuss k-contact reduction by a submanifold. Similar to the k-symplectic version, we need the k-contact orthogonal.
Okay. For a subspace WEX of TXM, what is its k-contact orthogonal WAX? The notation suggests it involves D.
Yes. Where X is the set of all vectors Vx in TXM such that dVx, Wx equals 0 for all W and will X. Remember, D is RK value, so this means dFex equals 0 for all and all would X.
Crucially, this orthogonality is defined using the 2-form D, not the 1 form itself.
That's a key difference from the k-symplectic orthogonal, which used it.
Okay. Now, theorem 4.6, k-contact reduction by a submanifold. What are the conditions?
Let N be a submanifold of M with inclusion A. N, AM. We look at the restrictions A and A. The conditions are 1, the kernels K and eukarya must have constant ranks on N.
Okay, well-behaved kernels.
2, let D be the intersection of these kernels, DAD. Let Fn be the foliation defined by D. The quotient space NFN must be a manifold, and the projection NFN must be a submersion.
So we quotient by the directions where both restricted forms vanish.
Yes, and there's one more crucial condition. 3, the Reeb vector fields, Ra, of the original manifold, M, must be tangent to the submanifold N at all points of N.
Ah, the Reeb fields have to live inside N. That seems important.
It is. If all these conditions hold, then the conclusion is the quotient space, NFN, EN, is itself a k-contact manifold.
It inherits a k-contact structure. And the reduced form relates back via EN is 80.
Exactly. Pulling back the reduced k-contact form EN gives the restriction of the original EN.
The proof sketch mentions analyzing the tangent space, TXN, using subspaces Y, Z, Re related to the kernels and Reeb fields. It sounds technically involved.
It involves carefully tracking how the defining properties of the k-contact structure, kernels, non-degeneracy, behave under restriction and quotienting, using the specific decomposition of the tangent space guaranteed by the conditions. The condition about Reeb fields being tangent is likely vital to ensure the reduced space also has well-defined Reeb fields.
Okay, that sets up the general reduction mechanism. Now, the main event, the k-contact MMW theorem. How do they approach it? Does it use the exact k-symplectic reduction theorem we just covered?
Yes, it does. It's quite clever. The bridge is theorem 4.9.
What does theorem 4.1 say?
It establishes a fundamental equivalence. MB is a k-contact manifold if and only if the product manifold RAM equipped with the RK-valued 2 form equals ds per m is an exact k-symplectic manifold of a specific type related to homogeneity.
Let's unpack AADM. Here's S as the coordinate on the R factor.
Yep.
RM is the pullback of E from M to RMM.
Correct. So S per m is an RK-valued 1 form on Rm. Its exterior derivative plus SS per m plus S per md is an RK-valued 2 form.
And ADS per m shows it's exact, with potential as S per m. So RAM becomes an exact k-symplectic manifold.
Exactly. This theorem allows us to lift any k-contact structure on M to an exact k-symplectic structure on the larger space RAM. This process is sometimes called symplectization.
Okay, so we can turn a k-contact problem into an exact k-symplectic problem. How does that help with reduction? Lemma 4.12 seems key.
Lemma 4.12 makes the connection for reduction. It relates the k-contact setup on M, action momentum map G value, to a corresponding setup on the lifted space RAM, an extended action, an extended exact momentum map G related value.
What does it relate specifically?
It shows that being a weak regular k value for G on M is related to a similar condition for J on RAM. It also shows that the technical conditions needed for k-contact reduction, like conditions 4.3, 4.4 related to kernels and Rivas fields, correspond directly to conditions 4.5, 4.6 needed for the exact k-symplectic reduction on RAM related to the k-action and kernels.
Wow. So this lemma essentially says, if the conditions for k-contact reduction hold on M, then the conditions for the exact k-symplectic MMW reduction, theorem 3.19, will hold on the lifted space RAM.
Precisely. It provides the direct translation between the two settings.
And it leads directly to the main theorem, theorem 4.14, the k-contact Marsden Meyer Weinstein reduction theorem. Yes. Now we can state it. Get in. 1. A k-contact manifold, MES with a k-contact, Lie group action A. 2. An ADUA equivariant k-contact momentum map, J. Equivariance is often assumed or follows in nice cases. 3. Is a weak regular k value of J. 4. The group K, defined just as before, Lie algebra K gay go, where J acts freely and properly on the level set rec. Notice the level set J is the same type as in the exact k-symplectic theorem. Yes, that choice was made precisely to match the structure that arises from the RSM lifting. Okay, given all those conditions, what is the conclusion of theorem 4.14? The conclusion is, the reduced space ME is itself a k-contact manifold. Fantastic. The quotient inherits the k-contact structure. And furthermore, there's a reduced k-contact form E on ME satisfying the usual pullback relation. I is E-egg, where I is inclusion and is projection. What about the Rivas fields? Do they survive the reduction?
Yes. Crucially, the theorem also states that the Rivas vector fields Ri of the original manifold M project down via the differential of the projection map to become the Rivas vector fields of the reduced k-contact manifold MFB.
That's really nice. The essential geometric features are preserved. How is this theorem proven?
The proof strategy is exactly what we set up. 1. Lift the k-contact manifold M and the action vep to the exact k-symplectic manifold RAMS produce and action vep using theorem 4.1 2. Construct the corresponding exact momentum map dummy theorem on RAM. 3. Use lemma 4.12 to verify that the conditions of the exact k-symplectic MMW theorem, theorem 3.1, hold for this lifted system. 4. Apply theorem 3.19 to get a reduced exact k-symplectic manifold RAM5. Show that this reduced manifold RAM has the structure of RAM, refers to manifold M, and that the reduced exact k-symplectic form implies, via the inverse of theorem 4.1, that M has a k-contact structure with the required properties.
That's a really elegant proof strategy, leveraging the known exact k-symplectic reduction machinery by temporarily moving to a higher dimensional space.
It is. It neatly sidesteps having to reprove all the symplectic reduction arguments directly in the context setting.
Example 4.15 illustrates this with a product of contact manifolds.
Yes. If you take M1 HAAMK, where each ma is a standard contact manifold, you can form a k-contact manifold using AAJ Pragia. They consider a specific Lie group action and calculate the k-contact momentum map. Then they show how theorem 4.14 applies to reduce this product structure under the symmetry.
And theorem 4.16 extends this to Hamiltonian systems. We have a G-invariant k-contact Hamiltonian system, MHA.
Yes, and if the conditions for the k-contact MMW reduction, theorem 4.14, are met, and if the associated k-contact Hamiltonian k-vector field XH is tangent to the level set BIA and is also invariant under the reduction group K, then X projects down to a well-defined k-contact Hamiltonian k-vector field Xan on the reduced manifold M, and this reduced vector field corresponds to a reduced Hamiltonian function H induced by H.
So the dynamics reduces consistently along with the geometry.
Exactly. Symmetry reduction works for the Hamiltonian dynamics too.
The paper then gives several more examples, 4.17, 4.118, 4.19. What do they show?
Example 4.17 looks at coupled damped strings, formulating it as a two-contact system and performing a reduction to get the dynamics on a lower dimensional k-contact space. Example 4.18 takes R10 with a specific two-contact structure and a 3D abelian group action, calculates the momentum map, and describes the reduced manifold.
And 4.19.
Example 4.19 specializes the k-contact MMW theorem to K1, the standard contact case. They apply it to the spherical cotangent bundle STQ, any shoe, go TQ R+, where R plates acts by scaling fibers, using the R+ action itself for reduction. They show this recovers known results about reduction of contact manifolds related to homogeneous symplectic manifolds and connects to Willett's earlier work on contact reduction.
So it shows their general k-contact theorem correctly reproduces known results in the simpler K1 case. That's an important consistency check.
Absolutely. These examples are crucial for building confidence in the theorem and understanding its scope and how to apply it. They make the abstract theory much more concrete.
Okay. The paper then has a section comparing this new k-contact reduction framework to previous work by Albert, Willett, Grabowski, and De Leon. Why dedicate a section to this?
It's standard and important practice in scientific papers. It achieves several things. First, it situates the new work within the existing landscape. How does it relate to, build upon, or differ from what came before?
Right, providing context.
Second, as the authors mentioned, they found what they believe were some inaccuracies or limitations in earlier results. This section allows them to discuss those issues explicitly and justify why their new approach might be more general or robust.
So positioning the work and also addressing potential issues in the literature, how do they start the comparison?
They first recall the well-known correspondence, Theorem 5.1, between contact manifolds K1 and symplectic Reed principal bundles, the symplectization idea we saw. Some earlier methods use this heavily. Then they summarize Willett's contact reduction theorem, Theorem 5.2. A key condition in Willett's theorem is an algebraic one on the Lie algebra, Ker plus GG, where G is the Lie algebra of the stabilizer G.
Okay, a specific technical condition.
Yes. They also summarize Grabowski and De Leon's approach, Theorem 5.3, which uses symplectic covers.
Then they get into the critique.
Yes. They point to a specific theorem, Theorem 1.1 in reference 36, and argue that its identification of the reduction group might be incorrect if Willett's condition, Ker plus GG, fails. They suggest the calculation of the symplectic orthogonal in that proof might be flawed, referencing one of Willett's own examples, example 3.7.
Do they provide their own counterexample?
Yeah. Yes. They analyze the action of SL2 on the contact manifold M equals TSL2 ER. They calculate the momentum map and show that applying the reduction method from 36 leads to a reduced space whose dimension doesn't match what's expected for a contact manifold, indicating a potential problem with that method in this case.
So they use a concrete example to highlight the issue they identified.
Exactly. This leads them to propose a corrected version of Grabowski and De Leon's theorem, which they present as their Theorem 5.4.
Okay, so they've addressed specific points in the previous literature. How do they compare their own main theorem, Theorem 4.14, to these earlier ones?
They use more examples. First, one on R7 with a GL2 action. They show Willett's condition, Kellier plus GEG, fails here, so Willett's theorem isn't directly applicable. They suggest their Theorem 4.14 might still work, though they don't fully verify it.
So highlighting a potential advantage in scope.
Then another example with an H2AR action. Again, Willett's condition fails. They then show that applying the method from 36 leads to an even-dimensional reduced space, which cannot be a contact manifold. Contact manifolds are always odd-dimensional. This clearly shows a limitation of that approach.
That seems like a significant point. Their method guarantees a k-contact result, while others might not.
Exactly. They also mention that some previous methods could result in one-dimensional reduced spaces, which aren't typically considered contact manifolds in the standard sense. They conclude by reiterating that their Theorem 4.14, using the group K and the level set, say rec, provides a more generally applicable approach that seems to avoid these pitfalls.
This careful comparison really strengthens their claims about the advantages and generality of their new theorem.
It does. It's crucial for establishing the contribution and placing it accurately within the field.
So, as we start to wrap up this, well, incredibly deep dive, what would you say are the main takeaways, the real headline results from this paper?
I think the biggest achievement is definitely extending the Marsden Meyer Weinstein reduction framework to co-orientable k-contact manifolds. That's a significant step forward, especially for studying dissipative systems using geometric methods.
And the generality of their theorem seems key too, right? Both the submanifold reduction version and the MMW version.
Yes. Their approach using the K-group seems to handle cases where previous methods, like Willett's or the one critiqued from 36, might run into trouble or require restrictive conditions like Ker plus GG.
The examples were really helpful too. Seeing it applied to product manifolds or the damp strings makes the abstract theory much more tangible.
Absolutely. Those illustrations are vital for showing the theory isn't just abstract mathematics, but has potential applications to concrete physical or mathematical systems.
And they even pointed towards future work.
Yeah, they mentioned generalizing to non-coorientable k-contact manifolds, which sounds challenging but interesting, and also developing orbit reduction techniques specifically in the k-contact setting, which is another standard type of reduction.
So it opens doors for more research.
Definitely. This work feels like it solidifies k-contact geometry and its reduction theory as important tools, particularly for non-conservative systems, and provides a foundation for further exploration.
It really highlights the power of these geometric methods for tackling complex problems.
It certainly does.
Well, that was genuinely a deep dive. We went through a lot of definitions, theorems, and intricate arguments there. Thank you so much for navigating us through it all.
My pleasure. It's fascinating material.
And thank you, our listener, for joining us on this exploration of Marsden Meyer Weinstein reduction for k-contact field theories. If this has piqued your interest and you want to grapple with the full mathematical rigor,
we definitely recommend checking out the original paper by De Lucas, Rivas, Vilariño, and Zawora, and the references therein.
Absolutely. There's always more depth to explore. Until our next deep dive, keep questioning, keep learning.
Welcome to the deep dive. Here, we don't just skim the surface. We take source materials, maybe articles, research papers, you name it, that you want to understand inside and out. And we really, we dive deep.
That's the idea. No shortcuts on understanding, just a focused exploration to get you completely up to speed.
And today we're tackling a research paper suggested by a listener. It's titled Marsden Meyer Weinstein Reduction for K-Contact Field Theories. The authors are Javier De Lucas, Xavier Rivas, Silvia Vilariño, and Bartosz M. Zawora.
Right, from the University of Warsaw and the Universitat Rovia i Virgili. They're delving into some pretty sophisticated mathematics here, extending a classical reduction technique, MMW reduction, into new territory.
Exactly. So our mission today is to unpack this paper piece by piece. We'll start with the fundamentals, the geometry of k-symplectic and k-contact manifolds. These are the spaces these theories live in.
Then we'll get into the reduction theorems themselves. First, how MMW reduction works for what are called exact k-symplectic manifolds.
And then the core contribution, adapting this MMW reduction for k-contact manifolds. These are particularly interesting because they often describe systems where energy isn't conserved, like systems with friction or damping.
Yeah, which makes them relevant for, modeling more realistic physical situations. And finally, we'll look closely at how this work compares to what's been done before in contact reduction. There have been other attempts, and understanding the differences is key.
So if you're ready for a thorough exploration, let's get started. Where do we begin? The paper starts with k-vector fields.
Right, let's lay the groundwork. Imagine you have a manifold M. Think of it as your configuration space or phase space. Locally, it looks like familiar Euclidean space, Rn, but globally it can be curved or connected in complicated ways.
Okay, standard manifold concept.
Now, a regular vector field assigns a single tangent vector like a velocity to each point. A k-vector field, on the other hand, assigns a k-tuple of tangent vectors to each point.
So k different directions or velocities at every single point.
Precisely. Formally, it's a section of the direct sum of k copies of the tangent bundle, Tm a jure, Tm k times. We can just think of it as an ordered set x, x1, x2, xk, where each exo is a standard vector field on M.
Okay, and how do these generate motion or describe evolution?
That involves the idea of an integral section, but first we need the first prolongation of a map. Suppose you have a map that goes from Rk, k-dimensional Euclidean space, into our manifold M.
So T is a point in M where T1, Tk is a point in Rk.
Exactly. The first prolongation, often written, bundles together the point with the partial derivatives of with respect to each of the variables T1 through Tk. It actually tells you where you are and how you're moving in each of the k directions defined by Rk.
Like the position and velocity in k dimensions mapped onto the manifold.
Sort of, yeah. Now, an integral section of our k-vector field x, x1, xk, is a map like the one we just described, such that its first prolongation phi matches the k-vector field x evaluated at the point.
So the velocity components of the map have to equal the components of the k-vector field at that location.
That's it. This condition actually spells out a system of partial differential equations, or PDEs, specifically Sx xt, for each off from 1 to k.
Ah, okay. And for these PDEs to have nice solutions, for the k-vector field to be integrable, what do we need?
We need the component vector fields to commute. That means the Lie bracket xec must be 0 for all pairs sec.
The classic commutativity condition. Following x and then x gives the same result as following xs then x.
Precisely. If they commute, the system is integrable, and we can find these integral sections. Okay, that's k-vector fields. Now let's transition to k-symplectic geometry.
Right, the structure of the space itself.
We start with an RK-valued 2 form. Just like a k-vector field was k-vector fields, this is essentially k-standard 2 forms. And is 1, oak, all defined on our manifold. Let's call it P now.
And a 2 form takes 2 tangent vectors and gives a number, so this gives k numbers, a vector in arc.
Exactly. Now, a k-symplectic manifold, P, is a manifold P equipped with such an RK-valued 2 form that has 2 key properties. First, it must be closed. D equals 0. This means applying the exterior derivative to U gives 0.
Analogous to the closed condition in standard symplectic geometry.
Yes. And second, it must be non-degenerate. This non-degeneracy condition is a bit stronger here. It means that if you take a tangent vector v and OVV equals 0 for all other tangent vectors u, and this holds for all k components su, then v must be the 0 vector.
So it's not enough for just one component form POO to detect non-zero vectors. The whole bundle has to be non-degenerate collectively.
Yeah, got it. It ensures the form is sensitive in all directions across all k components. Now, sometimes we add more structure. A polarized k-symplectic manifold, P, V. Here, V is an integrable distribution.
A distribution meaning a choice of subspace within each tangent space.
Right, smooth choice. V has to be integrable, meaning vector fields lying within V form a Lie algebra, and crucially, the k-symplectic form must be 0 when restricted to V. So V1, V2 equals 0 if both V1 and V2 are in V.
Okay, so V is like a special subspace where the symplectic form vanishes.
Exactly. And just like in standard symplectic geometry, there's a Darboux theorem. The k-symplectic Darboux theorem says that locally, on a polarized k-symplectic manifold, you can always find coordinates as C, right? It goes from 1 to n, from 1 to k, such that all looks very simple.
The canonical form.
Yes. A case find a likey, teki, Harriettia. Here A are the standard basis vectors in RK. It means locally, all these manifolds have the same fundamental structure.
That's powerful. It simplifies local analysis enormously. Are there standard examples?
A key one is built from the cotangent bundle. If Q is a manifold, our configuration space, TQ is its cotangent bundle, phase-space positions, and momenta. We can take A copies of this, bundle together the Whitney sum KQ equals TQAQ.
So K sets of momenta for each configuration.
Right. This KQ comes with a natural k-symplectic form, 2TQ, built from the canonical symplectic forms on each TQ copy. It also has a natural polarization V, which is related to the projection back down to Q. In local coordinates key, positions key, momenta P for the th copy, this canonical form is 2TQ kuk, the key KTP. Key, it looks just like the Darboux form, doesn't it?
It does, yeah. Very clean. Okay, so we have the stage, the k-symplectic manifold. How do we put dynamics on it? Hamiltonian system.
Exactly. A k-symplectic Hamiltonian system is a triplet, PIH, where P is our k-symplectic manifold and H is a Hamiltonian function, a smooth, real-valued function on P, often representing energy.
Standard Hamiltonian idea.
Now, we define a map, denoted flat omega. It takes a k-vector field x, x1, xk, and maps it to a 1 form, a cotangent vector. The definition is exz, all x a z, where z is any other tangent vector.
So it uses the k-symplectic form to convert the k-vector field into a 1 form.
Yes. Then, the k-symplectic Hamilton to Donderwell equation is simply Xio x dh. Here, dh is the exterior derivative of the Hamiltonian function h.
Ah, so this equation links the dynamics, represented by the k-vector field x, to the energy landscape, represented by dh, via the k-symplectic structure.
That's the heart of it. A k-vector field x satisfying this is called the k-symplectic Hamiltonian k-vector field. It's unique up to adding a k-symplectic gauge k-vector field that's any k-vector field y such that Xio y is 0y.
So there's some freedom, some gauge freedom in choosing x.
Right, and in those Darboux coordinates, y, if you have a Hamiltonian hxy, the components x of the Hamiltonian k-vector field x take a specific form, x,
Yeah.
ikia, summed over I, looks familiar, right?
Very much like the standard Hamilton's equations component.
Indeed. Now, a crucial point. This Hamiltonian k-vector field x isn't automatically integrable. Its components x might not commute.
Ah, okay. So just finding x doesn't guarantee solutions in the form of integral sections.
Correct. But if x is integrable, meaning x, this is 0, then its integral sections, the maps from RK to P, are solutions to what are called the Hamilton de Donder-Weil field equations. These equations govern how fields evolve over the K parameters, which might represent space and time.
So integrability of the Hamiltonian K-vector field is the key condition for getting actual field evolution obeying the Hamiltonian principle.
Exactly. Okay, that covers the k-symplectic side. Ready to switch gears to k-contact geometry?
Let's do it. Sounds related but distinct.
It is. K-contact geometry often arises in systems with dissipation, or systems described using homogeneous coordinates. We start with something called a generalized subbundle D of a vector bundle E over M. It's basically a smoothly varying assignment of subspaces dp within each fiber E.
Okay.
If the dimension, the rank of dp, is constant everywhere, we call D a regular subbundle. The corank is just the fiber dimension minus the rank.
Standard definitions.
Now consider an RK-valued 1 form, E, up equals 0, 1, E1 more D. Its kernel is the set of all tangent vectors V, such that EOV, meaning E1, equals 0 for all O. This kernel is a distribution.
The subspace annihilated by E?
Yes. Now, a K-contact form on some open set U and M is an RK-valued 1 form that has to satisfy 3 specific conditions. 1, AFL must be a regular distribution with current K. 2, the kernel of its exterior derivative, kerD, must also be a regular distribution but with rank K. 3. The intersection of these two kernels, Kerr and Akerfield, must contain only the 0 vector at every point.
Wow, okay. Those are quite specific structural requirements. So unlike k-symplectic, where D is non-zero and its kernel plays a big role.
Precisely. The non-vanishing D is characteristic of contact geometry. A manifold M with such a form is a co-oriented K-contact manifold. If we also have an integrable distribution V inside Kerr, like in the k-symplectic case, we call it a polarized co-oriented K-contact manifold.
Yeah. And you mentioned this relates to standard contact geometry.
Yes. A one-contact manifold, K1, is just a standard contact manifold. The paper assumes K1 implicitly in some definitions, or at least avoids dimension 1 issues. A really important feature of these manifolds is the existence of unique Reeb vector fields.
Reeb vector fields, I've heard of those in standard contact geometry.
Yeah, here we get K of them, R1 right, RK. They're uniquely defined by 2 sets of equations involving the interior product of T. 1, Rered Reeb field, Kronecker delta. 1, Rered grotto, 0, 0, 0 otherwise. 1, Rered bus, Reed delta. It's all 0 for all but.
So the auth-Reeb field is kind of dual to the auth component of E, and it lies in the kernel of D.
Exactly. And furthermore, these Reeb vector fields all commute with each other. Ribert-Brock is non-zero everywhere. They form a natural frame for the kerD distribution.
They seem really fundamental to the structure.
They are. Similar to the k-symplectic case, we can define a map, flat, eta, for a k-vector field X equates x1, xk. AX is a 1 form defined by E so Y on die K. A E gauge k-vector field is 1 in the kernel of R.
Okay, analogous map. Is there a canonical example like the cotangent bundle sum for k-symplectic?
There is. We take the same Whitney sum, M, E, K, T, Q, but now we cross it with RK. So M at G is RK, E share RK, T, Q, A, K, okay. Let Z be coordinates on RK. The natural K-contact form is EQ, A, psi, Ia, where psi is the pullback of the Louisville 1 form from the F copy of TQ.
Involving the Z coordinates now.
Yes. This manifold, MEQ, is a polarized, co-oriented K-contact manifold. The polarization V is essentially the tangent space to the arccat factor. You can work out KKQ and DQ and find that the Reeb vector fields are simply Rakage.
Nice and concrete. And is there a Darboux theorem here too?
There is. The K-contact Darboux theorem for polarized co-oriented K-contact manifolds guarantees that locally you can always find coordinates K such that the K-contact form becomes EGT Taiki Yay.
Again, local simplification to a standard model. Very useful. Now, Hamiltonian dynamics in this setting.
Right. A K-contact Hamiltonian system is MEH, where H is the Hamiltonian function. The dynamics for a map RKM are given by the K-contact Hamilton de Donder-Weil equations. They look a bit different. 1, Ifadia, the S-ways, sum over R implied. 2, EH, sum over implied. Here is the first prolongation, and Rhi is the derivative of F-Re along the F-Reeb field.
Okay, those look more involved than the k-symplectic ones. They directly involve the Reeb fields and the Hamiltonian itself on the right-hand side.
They do. In Darboux coordinates, they expand into a specific set of PDEs, equation 2.6 in the paper. We can also write equivalent equations for a k-vector field X. equation 2.7. An integrable x satisfying these equations will have integral sections that satisfy the map equations we just saw.
And the paper gives an example.
Yes, the coupled strings with damping example, section 2.5.1. They show how a two-contact form, K2, naturally describes this system. And applying the K-contact Hamilton to Donner-Weil formalism leads directly to the expected damped wave equation, equation 2.13.
That's a great illustration. It really shows the power of this framework for non-conservative systems. Okay, so we have the geometric setup for both k-symplectic and k-contact cases. Now, let's get into the reduction.
Right. MMW reduction, Marsden Meyer Weinstein reduction. It's a cornerstone technique in geometric mechanics, originally for symplectic manifolds. The idea is, if you have symmetries, you have conserved quantities, and you can use these to reduce the complexity of your system to find a smaller space that captures the essential dynamics.
Dividing out by the symmetry.
Essentially, yes. The paper extends this to k-symplectic and then k-contact settings. Let's start with exact k-symplectic manifolds. Recall, this means our k-symplectic form can be written as a day for some rk-valued 1 form.
Okay, O's exact.
Now, suppose we have a Lie group G acting on our manifold P via an action now. If this action preserves the 1 form, a areo, meaning areo for all G and G, we call it an exact k-symplectic Lie group action.
The symmetry respects the potential form.
Exactly. For such an action, we can define an exact k-symplectic momentum map, J. It's a map from P to GK, the space of k-tuples of elements in the dual of the Lie algebra G of G.
So it maps points in our space P to k-tuples of momenta associated with the symmetry group G.
That's the idea. It's defined by the condition. For every element form in the Lie algebra G. Here, areo is the vector field on P generated by the action of air.
The momentum map captures how the 1 form changes along symmetry directions.
Precisely. Now, slightly different scenario. If the action A only preserves the 2 form A, we call it a k-symplectic Lie group action, we can still define a k-symplectic momentum map J from P to GK, but now the condition is areos to GA.
Related, but involves O and the exterior derivative D on the right.
Yes. An important property, especially for the exact momentum map J, is add K equivariance. This means the momentum map transforms nicely under the group action. Add J, where add is the coadjoint action of the group element G. This property is vital for the reduction.
It ensures consistency between the group action on P and its induced action on the momentum values. Okay. So how do we use this map to reduce the space?
The core idea is to look at a level set of the momentum map J where the some fixed value in JK. We want to quotient this level set by the action of a subgroup of G that preserves Uth. But we need conditions for this quotient to be a nice k-symplectic manifold itself.
What are the potential problems?
Well, the level set may not be a smooth submanifold, might not be a regular enough value, and the quotient space might not inherit a well-defined, non-degenerate k-symplectic form. The MMW theorem provides the conditions to avoid these issues.
Okay. The paper first discusses a more general reduction by a submanifold S, theorem 3.8.
Right. For the main theorem, it introduces the k-symplectic orthogonal WPO of a subspace WAP Euro. This is the set of all vectors Z, such that tau WZ equals all W in WAP and all BUM.
Like the orthogonal complement, but using the k-symplectic form.
Exactly. Theorem 3.8 says if S is the submanifold where the kernel of the pullback of Kuro has constant rank, and if the quotient SFS, where Fs is the foliation by the integral manifolds of this kernel, is a manifold, then this quotient inherits a k-symplectic form S.
A general way to get a reduced k-symplectic structure if the kernel behaves nicely.
Yes. Now, the main MMW theorem for exact k-symplectic manifolds, the theorem 3.1, later detailed in 3.99, applies this idea to the level set S J1us. It requires to be a weak regular k value of J, meaning the derivative of J is surjective at points in the level set. It also involves the subgroup G of G that leaves invariant under the coadjoint action.
The symmetry group of the momentum value itself.
Right. The theorem states that if certain conditions, specifically 3.5 and 3.6 in the paper, relating tangent spaces of orbits to kernels hold, then the quotient space P is a k-symplectic manifold with the unique induced formor.
And those conditions, 3.5 and 3.6, basically ensure everything fits together correctly, that the quotient is smooth and the form is non-degenerate.
That's the essence. They ensure that the directions you quotient by are precisely the degenerate directions within the level set. The paper then goes into a detailed proof, defining Lie subalgebras Co and subgroups K, proposition 3.12, lemma 3.13, proving certain subspaces are symplectic, proposition 3.18, and finally, stating and proving the full theorem, theorem 3.19. It's quite technical, involving several lemmas about linear maps and kernels, lemmas 3.15, 3.17, 3.20, 3.22, theorem 3.23 wraps it all up.
Okay, a thorough treatment for the exact k-symplectic case. Now, the main event, extending this to k-contact manifold, how does that work?
This is section 4, the core of their contribution. They first define the k-contact momentum map. If E is a k-contact Lie group action on A, meaning AEA, then the k-contact momentum map, A maps M to GK and satisfies AE for all A can G.
Similar definition to the exact k-symplectic one, but using A instead of...
Exactly. And a key property follows. They also define G-invariant k-contact Hamiltonian systems, where both A and the Hamiltonian H are G-invariant.
Makes sense. Is there a k-contact reduction by submanifold theorem too?
Yes, theorem 4.6. It's analogous to the k-symplectic one. You need a submanifold N where the ranks of care and carity are constant. You also need the quotient NFN, where Fn relates to the intersection of those kernels, to be a manifold. And critically, you need the Reeb vector fields Rhi to be tangent to N.
The Reeb fields have to stay within the submanifold.
Yes. If all that holds, the quotient, NFN, AN, inherits a k-contact structure. It details the dimensions and how the tangent space splits up.
Okay, now for the k-contact MMW theorem itself, theorem 4.14. How do they prove it?
They use a really elegant connection. Theorem 4.1 shows that a manifold M is k-contact if and only if the product manifold P equals RAM, equipped with the RK value 2 form, all equals DSPEMA, is an exact k-symplectic manifold. Here S is the coordinate on R, and PRME is pulled back to the product space.
Wow. So they can embed the k-contact problem into the exact k-symplectic framework they just developed.
Exactly. They prove IDS PRME is closed, it's exact, and non-degenerate. Then they lift the G action A on M to an action A on P, goes RAM, acting only on the M factor. They define a corresponding exact k-symplectic momentum map, GRAP, related to the k-contact momentum map, G on M, lemma 4.12.
So they can apply the k-symplectic MMW reduction to P.
Precisely. They show that the necessary conditions for k-symplectic reduction on P, conditions 3.5 and 3.6 from before, now labeled 4.5 and 4.6 in this context, are equivalent to a new set of conditions, 4.3 and 4.4, stated purely in terms of the k-contact manifold M, the map J, and the subgroup K. This is lemma 4.13.
What do conditions 4.3 and 4.4 look like, roughly?
Condition 4.3 basically says the tangent space to the orbit of the subgroup K within level set J must exactly match the intersection of the tangent space to the level set and the kernel of D restricted to the level set. Condition 4.4 is similar, but involves kickery. They ensure the reduction respects both the E and D structures.
So, if these k-contact conditions hold, the k-symplectic reduction works upstairs on RAM, and this guarantees
that the resultant quotient space M, the KK, is a well-defined k-contact manifold equipped with a unique reduced k-contact form. Theorem 4.14 formalizes this, and Figure 2 shows a nice commutative diagram relating the spaces and maps.
That's a very clever strategy, leveraging the known symplectic result. Does this also work for Hamiltonian systems?
Yes. Theorem 4.16 shows that if you start with a G-invariant k-contact Hamiltonian system, MEH, the reduction process yields a reduced k-contact Hamiltonian system, MEH, where H is the induced Hamiltonian on the reduced space. The dynamics are consistent.
And the paper gives examples of this k-contact reduction.
Several good ones. Example 4.15 looks at a product of k-standard contact manifolds and shows the reduction works as expected. Example 4.17 revisits the damped coupled strings, applies a symmetry reduction using a theorem, and finds the reduced two-contact Hamiltonian system.
Applying it back to the physical example.
Exactly. Then examples 4.18 and 4.19 focus on the K1 case, standard contact reduction. Example 4.18 uses R10 with a specific contact form and group action. Example 4.19 deals with the spherical cotangent bundle of a Riemannian manifold, showing how it fits into this framework and reduces correctly.
Provides concrete illustrations of the abstract machinery. Okay, the final major section compares this approach to previous work on contact reduction. What's the main takeaway there?
This section is important for understanding the context and potential advantages of their method. They start by recalling the link between contact manifolds and line symplectic manifolds via Rev bundles, theorem 5.1. Then they review two main prior approaches. First, Willett's contact reduction, theorem 5.2, which works under a specific condition, care plus G, where is the momentum value. This condition isn't always met.
So Willett's theorem is limited.
Inapplicability, yes. Second, they discuss a method from a paper referred to as 36, Theorem 5.3, which uses a symplectic cover approach and doesn't require Willet's condition. However, the authors here identify some technical issues with Theorem 1.1 and 36.
What kind of issues?
They argue that the way the reduction group and the symplectic orthogonal are calculated in 36 can be incorrect, especially when Willet's condition fails. They provide a concrete counterexample using TSL2 HLR to show that the kernel identified for reduction in 36 differs from what their more general analysis yields.
So their method potentially handles cases where the older ones might get the reduction group wrong.
That seems to be the claim. Example 5.5 compares their method directly with 36 and another related work, 65 on R7, showing different reduction groups emerge. Example 5.6 provides a case where Willet's condition fails, and they argue their symplectic cover approach, via REM, correctly handles the reduction.
Do they offer a correction to the theorem from 36?
Yes, they present their Theorem 5.4 as a corrected version of Theorem 5.3 from 36, emphasizing the proper calculation of the relevant subspaces and group. They also mention a subtle issue in 3665, where the reduced space could be one-dimensional, which technically isn't a contact manifold by some definitions.
Okay, so they're not just extending MMW, but also refining and correcting aspects of previous contact reduction literature.
Exactly. It's a careful piece of work that aims for both generalization and rigor, building upon and clarifying earlier results.
Right. So summarizing the achievements. They've extended MMW reduction to co-orientable K-contact manifolds, provided a general reduction theorem by submanifolds for K-contact structures, and established clear conditions for when the reduced space is indeed K-contact using that clever RAM trick.
That captures it well. And the motivation, as we discussed, is that K-contact geometry is a powerful tool for non-conservative systems. So having a robust reduction technique for these systems is significant.
And looking ahead, what did they suggest as future work?
Two main avenues mentioned were generalizing this to non-coorientable K-contact manifolds, which sounds considerably harder because the RAM trick relies on co-orientability.
Right, that connection might break down.
And second, applying their framework to study orbit reduction specifically in the standard K1 contact setting, potentially offering new perspectives even on classical contact reduction.
This has certainly been a deep dive. We've gone through the definitions, the theorems, the proofs, the examples, and the comparisons. Hopefully, for you listening, this gives a really solid grounding in the paper's content and significance.
Absolutely. It's complex material, but understanding how symmetries simplify dynamics, even in these generalized geometric settings like K-contact manifolds, is fundamental. It opens doors to analyzing complex field theories and dissipative systems more effectively.
So the final thought to leave you with. Where might these techniques reducing complexity by understanding symmetry, even in non-energy conserving situations, provide a breakthrough in understanding the complex systems you study or encounter? What hidden simplicities might be waiting to be revealed? Thanks for joining us on the Deep Dive. Welcome back to the Deep Dive. Our mission here is pretty straightforward. We take dense, complex information, the kind you usually find buried in academic papers, and we distill it down. We want to give you the essential insights, a real understanding of what matters.
And today, we're tackling something, well, particularly intricate but really fascinating. We're diving into Marsden Meyer Weinstein reduction.
Right, but specifically how it applies to something called K-contact field theories.
Exactly.
Now, those terms, Marsden Meyer Weinstein, K-contact, I mean, they definitely sound like they belong in a pretty advanced math text.
I certainly did.
And, you know, they are, but that's why we're here.
Yeah.
Think of us as your guides. We'll start with the basics, the core geometric ideas, and then build up carefully to the reduction techniques themselves and why they're so important.
Yeah, and our main source for this deep dive is the research paper called Marsden Meyer Weinstein Reduction for K-contact Field Theories. It's a really detailed look at these ideas, and we'll be leaning heavily on its framework and the structures it lays out.
Okay, so what's the plan? What's our roadmap? We're going to start by building a solid foundation, looking at the geometry of k-symplectic and k-contact manifolds. These are the spaces we're working in.
The basic playground.
Then, from there, we'll dig into how reduction works for what are called exact k-symplectic manifolds.
That gives us some crucial tools.
Right, tools that will let us tackle the main event, the MMW reduction that's specifically built for K-contact manifolds, which is the core of the paper.
And we'll also take some time to see how this fits into the bigger picture, comparing it with other contact reduction theories out there, seeing what's new and what it clarifies.
Exactly. The goal is that by the end, you'll have a really thorough grasp of this whole area. Okay, so let's start at the beginning. Geometry of k-symplectic and k-contact manifolds.
Absolutely. So the paper starts, quite logically, with k-vector fields. Now, a standard vector field on a manifold M, you can picture it, right? It assigns a single direction, like a velocity, at every single point.
One arrow at each point.
Exactly. A k-vector field just takes that idea and says, okay, instead of one arrow, let's assign k arrows at each point, a collection of k-vector fields.
Okay.
So mathematically, you'd say it's a section of the direct sum of k copies of the tangent bundle, Tm over m. For any point P, a k-vector field X gives you a k-tuple of tangent vectors, x1p, x2p, xkp.
So not just one push, but potentially k independent pushes or directions acting at that point.
That's a great way to think about it.
Yeah.
Now, how do these relate to actual movement, to paths on the manifold? We need to look at maps from arc, that's k-dimensional space, into our manifold M. Let's call such a map from now.
Okay, a map from arc to M.
From that map, we can define its first prolongation. It's a new map, also starting from arc, but it lands in the direct sum of k copies of the tangent bundle.
So it's keeping track of more information.
Yes.
So.
At any point in Elbror gives you not just a position on the manifold M, but also all the partial derivatives of decay with respect to the k-coordinates of arc.
Yeah.
It captures the position and the velocity of arrival from each of the k-independent directions in arc.
Ah, okay. So S is the path, and S is the path plus the speed and direction information related to each input dimension.
You got it. Now, with that idea of the first prolongation, we can define an integral section of a k-vector field X. An integral section is just a map whose first prolongation matches the k-vector field X evaluated along the map itself. So TIR equals X.
Meaning the velocities of the map in those k directions perfectly match the k tangent vectors that the k-vector field X assigns at that point on M?
Exactly. The path perfectly follows the instructions laid out by the k-vector field X.
Okay, so X is a set of instructions across the manifold, and it is a way of actually following those instructions as we move through our parameter space, Rk.
A very good summary. Now, a really crucial concept here is integrability. When is a k-vector field X, x1, xkha? Integrable. It's integrable if and only if all its component vector fields G commute with each other.
Meaning the Lie bracket G, xj is 0 for all pairs I and j.
Precisely. Remember, the Lie bracket tells you if the flows commute, if going along xi, then xj gets you to the same place as going along xj than xi. For integrability, this needs to hold for every pair.
And the paper links this commutativity to the integrability of a system of partial differential equations, right? How does that work?
Yes. If you write everything out in local coordinates on M, the condition that F's is an integral section of X becomes a system of first-order PDEs for the components of S. The integrability of the k-vector field, the pairwise commuting, is exactly the Frobenius integrability condition needed for that system of PDEs to actually have local solutions.
Right, so the abstract algebra of commuting vector fields tells us if we can actually find concrete paths of these integral sections that follow the k-vector field's directions.
Okay, that makes sense for k-vector fields. Now let's switch gears slightly to k-symplectic geometry. What defines a k-symplectic manifold?
Okay, so a k-symplectic manifold is a pair, P. P is manifold, and a diamond is a special kind of differential form. It's an RK-valued differential 2 form, meaning it takes two tangent vectors and gives back a vector in arc.
Exactly. And for 2 to be symplectic, it needs 2 properties. First, it has to be closed, DO of 0. Its exterior derivative is 0.
Like in standard symplectic geometry.
Right, a generalization. Second, it has to be non-degenerate. For a standard 2 form, non-degeneracy means only the 0 vector gets sent to 0 when paired with everything else. Here, for non-degeneracy means if alju u 0 for all vectors v and for all components from 1k, then the vector u must be the 0 vector.
So O doesn't miss any directions. The closedness suggests some kind of local potential exists, and non-degeneracy means it pairs things up strongly.
That's the intuition. Then the paper introduces polarized k-symplectic manifolds, PO. This adds another piece of structure, an integrable distribution V.
A distribution, like a choice of subspace in the tangent space at each point.
Exactly. An integrable distribution V of a specific rank, let's say inc. The key property is that O restricted to V is 0. So if you take 2 vectors u and v both from V, then OUV 0z.
So V is a subspace where the k-symplectic form is internally trivial.
Yes, and integrability of V means these subspaces fit together smoothly to form actual submanifolds because the vector fields spanning V commute.
Okay, so the polarization V splits the tangent space, and integrability makes it geometrically well-behaved.
Precisely. And then comes a really powerful result, the k-symplectic Darboux theorem. It basically says that locally, all these polarized k-symplectic manifolds look the same.
Ah, the Darboux theorem, always simplifying things.
Exactly. It guarantees you can always find local coordinates, let's call them E, where O takes a simple canonical form, EO, GGA, DOG. Here, I runs from 1 to N, E runs from 1 to K, and E is just the standard basis for ARCA.
So no matter how weird it looks globally, zoom in and you find these nice coordinates where O looks standard. That's huge.
It is, and the paper gives a key example. The canonical k-symplectic structure on TKQ. That's the Whitney sum of k copies of the cotangent bundle TQ.
So you take the configuration space Q, look at its cotangent bundle positions and momenta, and then stack k copies of that.
Kind of, yes. At each point of Q, you have k sets of momenta. On this bigger space, TKQ, there's a natural RK-valued one form, KKQ, built from the standard Liouville one form on TQ.
And the k-symplectic form is just its exterior derivative.
Right, 2KQ, DKQ. And the paper gives the Darboux coordinates for this specific case. If Q has coordinates key, then the TKQ has coordinates key P, where pi is the momentum for coordinate key in the auth copy. And 2KQ becomes Ia de Pini D key Ia.
So this TKQ space with this canonical form serves as the local model for all polarized k-symplectic manifolds, like Euclidean space for geometry.
Exactly. And it is a polarized k-symplectic manifold itself, with the polarization given by the vertical vectors, so it's tangent to the momentum fibers. Okay, now Hamiltonian systems in this setting.
Right, k-symplectic Hamiltonian system.
It's a triplet, P, O, H. P is our k-symplectic manifold, is the form, and H is a smooth function on P, the Hamiltonian. Often represents energy.
So we have the phase space, PO, and the energy landscape, H. How does the system evolve?
Through the k-symplectic Hamilton to Donderweil equation. It looks like E psi x, Lx, dH.
VH is the gradient of the Hamiltonian, a one form. What's X and E?
X is the k-vector field we're looking for, the one that describes the evolution. And EA is a map, a morphism, that takes this k-vector field X, X1, Xk, and produces a one form. It essentially contracts each component G with the corresponding component E of the k-symplectic form and sums them up.
So the equation basically says the work done by the k-vector field X, measured by the k-symplectic form, equals the change in the Hamiltonian age, a generalized Hamilton's equation.
That's it. The paper also defines k-symplectic age k-vector fields. These are the x's that get sent to 0 by x, so kx equals 0. They don't affect the equation.
They're like non-physical directions of evolution.
In a sense, a k-vector field X that does solve AX is called a k-symplectic Hamiltonian k-vector field. And it's not necessarily unique, right? You can always add a gauge field.
Okay. And in those nice Darboux coordinates on a polarized manifold.
Yeah, the components X of the Hamiltonian k-vector field have a specific form involving partial derivatives of H with respect to J and lane. But crucially...
Can you guess? They aren't necessarily integrable.
Exactly. The X you find might not have commuting components, but integrability is what you need to find actual solutions, the integral sections.
Because the integral section is the path whose velocities match the k-vector field. If it's not integrable, you might not be able to find such a consistent path.
Precisely. Proposition 2.9 makes that link formal. It says if you do have an integrable k-symplectic Hamiltonian k-vector field X on a polarized manifold, that its integral sections it has are solutions to the Hamilton to Donderweil field equations, which are the PDE version for the MATLABs.
Okay, so the bridge is integrable k-symplectic Hamiltonian k-vector field integral sections of Collins solutions to the field equations. Got it. Now, let's make the jump to k-contact geometry. What's fundamentally different here?
K-contact geometry starts with a different basic object. It often involves generalized subbundles first. Think of a vector bundle, E over M. A generalized subbundle D is just picking a subspace dx inside each fiber X.
Just choosing subspaces.
Yeah. And it's smooth if you can locally find smooth sections that span dx everywhere. It's regular if it's smooth, and the dimension, the rank of dx is constant everywhere. Or, equivalently, the corank is constant.
Okay, so a regular generalized subbundle is a consistent way to pick subspaces in each layer.
Now, take an RK-valued differential one form on some open set U in our manifold M. This cororing defines a co-distribution, and its annihilator, core, is a distribution in the tangent bundle all vectors v where d equals 0 in Rk.
Right.
Now, for E to be a k-contact form, it needs to satisfy three key conditions. First, its kernel, core, must be a regular distribution with core rank.
So the dimension outside the kernel is k.
Yes. Second, the kernel of its exterior derivative, dd, must be a regular distribution with rank k. Remember, d is an Rk-valued 2 form. Its kernel consists of vectors v, such that dv(w) equals 0 for all w.
So ker-d has dimension k.
Correct. And third, the intersection of ker-d and ker-d must be only the 0 vector at every point.
Wow, okay. So specific conditions on the dimensions of the kernels of I or D, and they can't overlap non-trivially. That sounds quite restrictive.
It is. It enforces a kind of maximal non-integrability characteristic of contact structures. A manifold M with such an E is a co-oriented k-contact manifold. And if you add an integrable distribution V inside Birker with rank Inc.,
then you get a polarized co-oriented k-contact manifold, MV. Similar idea to the k-symplectic case.
Exactly. And the paper notes, importantly, that for K1, this just recovers standard contact manifolds.
Okay, and what about these Reed vector fields? They seem specific to k-contact.
They are very special. For a co-orientable k-contact manifold, MB, there's a unique family of k-vector fields, R1, 8, Rk, called the Reed vector fields. They're defined by how they interact with E delta.
How so?
Specifically, contracting rho with E gives the Kronecker delta bow, so E bride dia, and contracting rho with D gives 0.
So Rhi is orthogonal to day, and it picks out the auth component of 8.
Sort of, yes. Plus, these K-Reed fields must commute with each other. Rhi is the 0, and together they must span the K-dimensional kernel of day at every point. Their wedge product R1 SSA arc must also be non-zero.
So they're unique, they commute, they form a basis for core day, and they have this special relationship with R. That's a lot of structure tied up in them.
It is. Then, similar to before, there's a morphism Rhi related to data mapping K-tuples of vectors to TMR, and an E-gauge K-vector field is one in the kernel of EA.
Okay, and then example 2.14 gives a concrete picture.
Yes, a really important one. Consider M. AZQ, AIK, so K copies of TQ times RK. The paper defines a natural K contact form EQ on this space. It's EQA AIIQ.
Where Lees are coordinates on RK, EI is the basis, and pre-IQ pulls back the Liouville form from the ith copy of TQ.
Exactly. The paper then works out Curie Q DQ and shows the Reed vector fields are just Ryaza, the coordinate vector fields on ARC. It identifies a natural polarization V and confirms it's a polarized, co-oriented K-contact manifold. This is the key model.
So this construction provides a hands-on example of all the abstract definitions, something concrete, and I assume there's a K-contact Darboux theorem next. Theorem 2.15?
You guessed it. The K-contact Darboux theorem says that locally, around any point in a polarized, co-oriented K-contact manifold, MAV, you can find coordinates Ki Pi Za, where E looks like the canonical form from that example. E zatai pi diki asa.
Ah, so just like the k-symplectic case, we have a local standard form. Example 2.14 really is the canonical model.
It is. It simplifies local analysis tremendously.
Okay, so we have the geometry. What about k-contact Hamiltonian systems? How do dynamics work here?
Again, it's a triplet MH, with M being a co-oriented K-contact manifold, and H the Hamiltonian. The dynamics follow the K-contact Hamilton-Dodonder-Weil equations. For a map, UFT area M, these equations get a bit more involved.
How so?
They involve the first prolongation, contractions with D, contractions with an E itself, and the action of the Reed vector fields Rhi on the Hamiltonian H. For each A, the equation looks like E area D plus dia.
Definitely looks more complicated than the k-symplectic version. The E term and the Reed fields seem to add extra layers.
They do. It reflects a different geometry. In those Darboux coordinates, Q, pi, za, these map-based equations become explicit PDEs involving derivatives of various components and derivatives of H. The paper gives these in 2.6.
And like before, there's also a version for a k-vector field X.
Yes. The k-vector field-based Hamilton-Dodonder-Weil equations are EX, DH here. Remember area map to TMR? Here, the R component is 0. These equations are equivalent to relations involving X's components and H's derivatives in Darboux coordinates, given in 2.8, and proposition 2.18 again provides the link. An integral section of an integrable k-vector field X satisfies the map-based equations if and only if X satisfies the k-vector field-based equations.
But again, just having an x that satisfies the equations doesn't mean it's integrable or has integral sections.
Exactly the same caveat applies. Integrability is still the key to getting actual solutions, Patience.
Okay. And the paper wraps up this section with example 2.19, the coupled strings with damping. That sounds like a nice physical connection.
It is. It defines a specific two-contact manifold and Hamiltonian relevant to damped coupled strings. Working out the Hamilton to Dongerwile equations shows that for certain choices, they reduce to a damped wave equation.
Which is a standard physics equation.
Right. It beautifully shows how this K-contact framework can model non-conservative systems with things like friction or damping. So that covers the basic geometry and dynamics. Now we're ready for reduction.
All right, foundations laid. Let's dive into the reduction process itself, starting with exact k-symplectic manifolds. The paper immediately brings up k-symplectic momentum maps. What are these?
They're a generalization of the standard momentum maps you see in symplectic geometry. They pop up when you have a Lie group G acting on a k-symplectic manifold, P, in a way that preserves a.
That's symmetry action.
Exactly. The paper focuses mostly on what are called ad-k-equivariant momentum maps. These have nice transformation properties related to the group action. To define them properly, we need the Lie algebra G of the group G. Then GK is just k copies of G, and GK is k copies of the dual space G.
Okay, and the paper mentions some technical conditions like weak regular value and quotientable action. Why are those needed?
They're basically safety checks. They ensure the reduction process works smoothly and gives you back a nice geometric object. A weak regular value ensures the level set you use for reduction is a proper submanifold.
And quotientable.
That means the space of orbits under the group action is itself a smooth manifold. So taking the quotient makes geometric sense.
Got it. Now, the focus shifts to exact k-symplectic manifolds. Why the emphasis on exact?
An exact k-symplectic manifold is one where the k-symplectic form is the exterior derivative of some RK-valued one form. So, O stay. This is like a k-symplectic potential.
Okay, it has a potential.
Right. And if the Lie group action preserves this potential, meaning AA for all G and G, we call it an exact k-symplectic Lie group action.
And that lets you define something special.
Yes, an exact k-symplectic moment map, J. It maps from P to the k-fold dual of the Lie algebra. It's defined by relating the contraction of, with fundamental vector fields OP, generated by Lie algebra elements, to the pairing of the momentum map with S. So, S Ostehe.
Ah, so the potential lets you define the momentum map directly without needing a derivative, like in the general case.
Exactly. The standard k-symplectic momentum map J, where the action only preserves and not necessarily S, is defined by S A D S T.
Right, the exact case seems more direct.
It is. And crucially, Proposition 3.6 states that an exact k-symplectic momentum map J is always ad-k-covariant. That equivariance is really fundamental for the reduction to work properly.
Okay, so we have our exact manifold, an action preserving, and this nice ad-k equivariant momentum map J. How do we use these to actually reduce the system?
The paper mentions two main routes. First, reduction by a submanifold. You take a submanifold S inside P, restrict ofs to S, call it us. This restricted form might be degenerate, might have a kernel.
Directions within S that OS ignores.
Right. If that happens, under certain conditions detailed in Theorem 3.8, you can quotient S by the foliation defined by that kernel, call it FS, and get a new smaller k-symplectic manifold, SFS.
So you slice out a piece S, and if the form becomes degenerate on it, you shrink it further by dividing out those degenerate directions.
That's the idea. But the more central method for us is the Marsden Meyer Weinstein reduction, specifically Theorem 3.11 for k-symplectic manifolds.
The MMW theorem.
Yes. You start with a k-symplectic momentum map G for an action-preserving co. You pick a value in G, which is a weak regular k value for G. Then you look at the level set all points P, where GK.
Okay, the set of points with that specific momentum value.
Right. Now, you find the subgroup G of G that leaves unchanged under the coadjoint action. This subgroup G acts on the level set G. If certain conditions hold, linking kernels of GJ and PO, conditions of 3.5 and 3.6, and if the G action is free and proper.
Then the quotient space G is a k-symplectic manifold.
Exactly. You get a reduced k-symplectic manifold with a uniquely determined form.
That sounds very much like standard MMW reduction. Use the symmetry, G, to pick an invariant level set, then quotient by the symmetry that preserves that level set, G, to get a smaller space with the same kind of structure.
That's the core idea. Now, the paper introduces a modified MMW reduction specifically for the exact k-symplectic case. This modification is key because it's designed to connect directly to k-contact reduction later on.
Okay, what's different in the exact case reduction?
It involves identifying a specific Lie subalgebra cone inside G. It's defined using U and how the coadjoint action relates to. Proposition 3.1 shows it's a subalgebra.
So K is a special part of the Lie algebra related to our chosen momentum value.
Yes. Then K is the connected Lie subgroup corresponding to this subalgebra cone. Now, lemma 3.13 shows something important. For the level set, J using the exact momentum map J, the tangent space to the orbits of this group K is actually contained within the kernel of the k-symplectic form when restricted to that level set.
So the directions generated by K within the level set are invisible to the k-symplectic form.
Precisely. This suggests K is the right group to quotient by in this exact setting. The paper then goes through several technical lemmas, 3.14, 3.15, 3.16, 3.17, involving tangent spaces, symplectic with orthogonals, quotient spaces, and how the forms behave. These are all necessary steps.
Building up the machinery carefully?
Very carefully. It all culminates in Theorem 3.1c, the M&W reduction theorem for exact k-symplectic manifolds. It says if you have the exact momentum map, a suitable level set, and the action of K on this level set is quotientable.
Then the quotient Zawora gets a structure.
Yes, it gets a unique exact RK-valued 2-form ULC, and its exactness comes from a reduced 1-form. Lemma 3.22 gives conditions needed to ensure this reduced form is non-degenerate. So we have a way to reduce exact k-symplectic manifolds using this specific subgroup K.
Okay, so that provides the bridge. We've reduced exact k-symplectic manifolds using this K group. Now, how does this machinery apply to the main target, k-contact manifolds? How do momentum maps work there?
Right. So for k-contact, we need a k-contact Lie group action. That's an action of G on a co-orientable k-contact manifold that preserves the k-contact form itself. So k-contact form.
The action respects the k-contact structure.
Exactly. Given such an action, the k-contact momentum map G maps from M to G. It's defined by saying that for any EG in the Lie algebra G, the pairing EGB is equal to the RK-valued function you get by contracting the fundamental vector field Rchem with EG.
So again, the momentum map links the symmetry generator to how it interacts with the fundamental geometric structure, in this case, the k-contact form.
Precisely. Proposition 4.3 gives some useful properties. If F is a k-contact action, then GG-EG, and it gives a condition related to invariant Reeb fields for G to be ad equivariant. The paper also defines a G-invariant k-contact Hamiltonian system, M-AJ-H, one where the action preserves E's and the Hamiltonian H.
So a system where the symmetry respects everything important, geometry, momentum map, and energy. Ready for reduction.
Ready for reduction. Again, there's a brief mention of k-contact reduction by a submanifold, Theorem 4.6. Similar idea to the k-symplectic case.
Yeah.
You restrict E and D to a submanifold N, look at the kernel of these restricted forms, and quotient by the resulting foliation Fn. A key condition here is that the original Reeb fields raw must be tangent to N.
Okay, reducing by slicing and shrinking based on the k-contact structure on the slice.
Right. But the main event is the k-contact MMW reduction theorem, Theorem 4.14. And it uses a really clever trick involving Theorem 4.n.
What's the trick?
Theorem 4.n shows an equivalence between a k-contact manifold, M, and an exact k-symplectic manifold built from it, RRM, ESMPRM. Here, raw is positive reals, coordinate S, and pre-M pulls back to the product space. This is called symplectification.
Whoa, so you can turn your k-contact problem into an exact k-symplectic one on a slightly bigger space. That seems incredibly useful.
It is. It lets us leverage all the machinery we just developed for exact k-symplectic reduction. Lemma 4.12 then connects the dots. It relates weak regular values of the k-contact momentum map G on M to those of an extended k-symplectic momentum map G on rho M. It also shows the key conditions needed for good reduction in the k-symplectic setting. Conditions 4.5, 4.6 are equivalent to corresponding conditions in the k-contact setting. Conditions 4.3, 4.4.
So the conditions that make reduction work nicely on the symplectified space translate directly back to conditions on the original k-contact space.
Exactly. And that allows Theorem 4.14 to state the k-contact MMW reduction theorem. Under the right conditions, k-contact action, momentum map G, weak regular k-value, the reduced space M, J becomes a k-contact manifold, MB.
And note, it's the same subgroup K we used in the exact k-symplectic reduction.
Yes. That's the power of the simplification link. The reduced k-contact form comes from pulling back the original weight. And importantly, the Reeve vector fields on the reduced manifold M are just the projections of the original Reeve fields from M figure 2 in the paper shows a diagram illustrating all these connections.
This is fantastic. It takes a k-contact system with symmetry, uses the momentum map and the special subgroup K, and produces a smaller, simpler k-contact manifold that inherits the essential structure, including the Reeve fields.
That's the core achievement. And the paper backs this up with several really good examples. Example 4.15 looks at a product of K standard contact manifolds and reduces it. Theorem 4.16 shows how Hamiltonian dynamics reduce if you start with a G invariant K-contact Hamiltonian system. You get a reduced Hamiltonian system on M, and the flows project correctly.
So the dynamics simplify along with the geometry.
Yes. Example 4.17 revisits the coupled strings with damping, showing how this two-contact MMW reduction simplifies that physical system. Examples 4.18 and 4.19 give more mathematical illustrations, including reducing the cotangent bundle TQ via R plus action to recover the known contact structure on the spherical cotangent bundle.
Those examples really make it concrete. Seeing it applied to products, physical systems, and recovering known structures really drives home the utility of this K-contact MMW theorem. Okay, now a crucial part. Comparing this new approach to what came before in contact reduction, how does this work fit in?
Right. Section 5 is dedicated to that comparison, looking especially at work by Albert Willett in a specific paper referred to as 36. Figure 3 helps keep the notation straight.
Okay.
It starts by recalling the symplectification link, RAM. Then it mentions Albert's early work and its dependence on the choice of contact form. It summarizes Willett's generalization, highlighting his key condition for the reduced space to be contact, kicker plus G in G.
A condition relating the momentum value and the Lie algebra.
Yes. Then it outlines the approach in paper 36, which uses something called one-homogeneous symplectic Reeve principal bundles. This method works for non-coorientable manifolds too, and has slightly different conditions. However, the authors of our source paper note some potential issues or discordance between 36's results and Willett's, and also with their own findings, especially concerning the reduction group. They also mention that 36's technique doesn't seem to extend easily to the K-contact case we're interested in.
So this new work is positioned as not just an extension to K1, but also as potentially refining or correcting aspects of the K1 theory.
That seems to be a significant part of their contribution. They have a subsection titled On the Previous Contact Literature, where they directly engage with potential problems. They argue that theorem 1.1 and 36 might fail if Willett's condition K plus DG isn't met, referencing a counterexample.
Okay.
And critically, they suggest the reduction group used in 36 might not always be correct and should perhaps be the subgroup K that they identified via the exact symplectic reduction link.
The same K again.
Exactly. They illustrate this with an example. M equals TSL2 AR with a specific contact form and SL2 action. They calculate the reduced space using their K and find it's four-dimensional, which cannot be contact. But they state that theorem 5.3 from 36 claims a three-dimensional contact manifold results.
A direct contradiction.
Here so. They trace the potential issue in 36 to a calculation of a symplectic orthogonal. Based on this, they propose a corrected version of 36's theorem in their theorem 5.4, explicitly using their reduction group K.
Wow. Okay, so this isn't just extending, it's actively refining the K1 case by identifying the potentially more correct reduction subgroup K derived from the exact symplectic picture.
That's what the analysis suggests. They provide more examples, like RI with the GL2 action, where Willett's condition fails, so his theorem doesn't apply, but their method using K might still work. They do a similar analysis for an H2AR action on the same R. They also look at the symplectification of that example, and again highlight discrepancies in calculating the symplectic orthogonal compared to 36, reinforcing their argument for using K.
So, multiple examples pointing towards K as the key subgroup for reduction, derived consistently via the symplectification approach.
Precisely. They do mention a minor technical point about one-dimensional reduced spaces in 36, 65, but consider it less critical. The main thrust is the identification of K and the resulting refined reduction theorem.
This comparative analysis seems incredibly important. It really positions their K-contact MMW theorem not just as a generalization, but as providing a potentially more robust foundation, even for the standard K1 contact case.
Absolutely. So to wrap it all up, the paper successfully extends MMW reduction to co-orientable K-contact manifolds. This gives us a powerful tool for systems with symmetry, especially non-conservative ones.
And it seems to clarify and maybe even correct some aspects of the previous contact reduction literature along the way.
Indeed. The detailed comparison and the examples really highlight its contribution. The paper finishes by mentioning future directions, like tackling non-coorientable manifolds or further exploring orbit reductions for K1.
It underscores k-contact geometry as a vital framework for non-conservative systems and shows that there's still fertile ground for research.
Definitely. This work provides a solid advancement in that area.
Well, this has been an incredibly deep dive, really unpacking the intricacies of Marsden Meyer Weinstein reduction for k-contact field theories. We've gone from the geometric foundations all the way through the reduction theorems and the crucial comparisons with prior work.
It's dense material, but hopefully breaking it down step by step has made it more accessible.
Absolutely. We hope this detailed exploration has given you a solid understanding of this advanced topic. As always, the original paper is there if you want to go even deeper into the mathematics. Thanks for joining us on the deep dive.
Thank you for listening.